Okay, I think we can start the session. Welcome everybody to this session on haptics. My name is Gabriel Sackmann. I'm a professor for virtual reality with the University of Bremen, Germany. And it is my pleasure to be the host, the chair of this session. So we have 5 talks in this session. Just as a reminder to everybody, we will do the Q&A in one block at the end after all the talks. There's a Discord channel where I invite everybody to ask their questions anytime now. And without further ado, I would like to start with the first presentation. The first talk is on floor vibration, and it will be given by Sangjal Jong. He's a postdoc at the Canterbury University, the HIT Lab in New Zealand. So Sangjal, please, the floor is yours.
All right, thank you for the introduction. Hi, everyone. My name is... Okay. Thank you for the introduction. Hi, everyone. My name is Songchol Jung. I'm working at the HIT lab in New Zealand with a postdoc. I'm happy to give a presentation about our research. We would expect a fun and exciting experience in VR, but in reality, 40 to 70% of VR users may experience cyber sickness after around 15 minutes of the exposure. The symptoms are various. Cyber sickness induces nausea, vomit, disorientation, oculomotor disturbance, and sleepy. In order to resolve the problem, researchers have investigated why does cyber sickness happen, and the following theories has been suggested. And our research is based on sensory complex theory. Let's imagine that. For example, a VR user experiences a VR virtual driving simulation. After wearing HMD while sitting on a chair, the user can feel as if they are driving because of the visual stimuli. However, in the user's vestibular system, the organ does not feel anything because there is no physical movement. So conflict arises between the vision and the vestibular system, and thus, finally, it induces cyber sickness. Based on this scenario, we conjecture that if we provide minimally approximated the vibration stimuli through the floor to compensate for the missing vestibular stimuli, and then can you mitigate cyber sickness? In order to answer the research question, we developed a flow vibration generated via platform. We attached four butt kickers underneath the floor. They were connected to an amplifier and controlled the vibration type and intensity by a sound signal from the main computer. In our system, we used the Unity game engine to control the sound and render via scene. The user can hear the high-pass filtered engine sound through the headphone, and the user can feel the minimally matched low-pass filtered engine sound vibration through the floor. The gender-matched virtual driver drives the car along with a predefined course, while the participant seated on the passenger seat and experienced the driving around 7 minutes. We drove the 4 laps, and at each lap, the driver increased the car speed gradually. The study was conducted with between subject design. The one group experienced the simulation with a flow vibration, and the other group experienced the same simulation without the flow vibration with these three hypotheses. In this study, we collected objective measures such as heart rate, galvanic skin response, pupil size, and as a subjective measure, we collected cyber sickness level using simulation sickness questionnaire, discomfort level, and the sense of presence. Since the cyber sickness is related to the subjective physical and mental condition, we asked the participants to keep their best condition with guidelines that we provided a day before the study. This is a video for the whole procedure. For the first 1 minute in VR, we collected the visual signal as a baseline. We designed the course to have typical off-road driving characteristics that we included a frequent and substantial changes in vehicle pitch as the terrain rose and fell, and changes in yaw as the truck was steered along its course. Also, we rendered the scene with a high level of detail as we can see. At every level, we increased the car speed gradually, as I mentioned. So this is a lap first, and this is a second lap. This shows the lap three, and this shows the last one. Here are the results. While we did not find a significant difference in discomfort level, pupil size, and heart rate, we found a significant difference in galvanic skin responses. While the galvanic skin responses value in the vibration group, which are represented with a blue line, did not show meaningful variation, the value in a no vibration group, the red line, has increased after around 200 seconds. Numerically, the no vibration group shows a tendency to increase the value in this discomfort, heart rate, galvanic skin response, and pupil size. In addition, we observed a difference between around 170 seconds to 300 seconds in discomfort level. Regardless of the condition, both two lines shows incline at the end of the study, and thus we conclude that our platform successfully induced a proper level of cyber sickness. Also, we found a significant difference in oculomotor, which is a subset of the simulator sickness questionnaire. The vibration group has lower oculomotor disturbance compared to the no vibration group. For the sensible presence, we used a MEC special presence questionnaire, and as we expected, we did not find a significant difference in presence. For preference, we asked participants if they are willing to ride the simulator in the condition that they had not yet experienced after they complete the main part of the study. Except for one participant because of severe cyber sickness, 21 participants had the extra trial. The result shows that 21 out of the 21 participants revealed they prefer vibration experience to without vibration. Based on the result, we argued that we partially supported the first hypothesis, and our findings successfully supported the second and third hypothesis. Based on the motivation from the result, we implemented a mini version of the platform, which is the 1/6 scale of the original floor, as an example of a simple and cost-effective solution. In this study, we found limitations. First, even though we tried to generate vibration to compensate the missing sensory input to the vestibular system, there is actually no real way to know for sure if the vibration we supplied actually simulated the vestibular system in the right way. Second, during the study, we observed that two participants in the no vibration group tried to mitigate cyber sickness using their own strategies. Nevertheless, we still show the advantages of flow vibration, but there may still exist some hidden negative impact in the data. Based on the sensor complex theory, we provided a flow vibration in the passive driving simulation. We conclude that flow vibration that is at least minimally matched scenario can mitigate some indicators of cyber sickness. Thanks for your listening.
Okay, thank you very much, Sangchol, for your interesting talk. While we switch to the next presenter, I would just like to remind people that you can ask questions on Discord. And with that, we will switch to the next talk, which is on combining dynamic passive haptics and haptic retargeting. And the paper will be presented by André Zenner. He's a PhD candidate at the Saarbrücken University.
All right, thank you very much for the kind introduction, and hello everyone. I'm André Zenner. I'm a doctoral researcher at Saarland University and the German Research Center for Artificial Intelligence in Saarbrücken, Germany. And in the following, I'm happy to present to you the TVCG paper of my co-authors, Christine Ullmann, Antonio Krüger, and myself about combining dynamic passive haptics and haptic retargeting for enhanced haptic feedback in virtual reality. Our paper is concerned with two central challenges of proxy-based haptics for VR, a concept which leverages physical proxies to deliver haptic sensations during interactions with virtual environments. In order to achieve high-quality feedback, systems that employ proxy-based haptics need to solve the challenge of similarity by ensuring that the haptic props they are using are sufficiently similar in terms of their haptic properties to the virtual objects that they represent. Moreover, they need to solve the challenge of collocation by ensuring that proxies are spatially aligned with the virtual objects they represent to enable a seamless interaction. In our investigated scenario in this paper, we consider a VR system that uses proxy-based haptics to render the weight distribution inside a virtual stick. Our paper proposes and evaluates the combination of two different techniques for enhancing proxy-based haptics that each have individually been shown to be very successful in tackling the challenges of similarity and collocation, but that have only been studied in isolation in the past. And the first of those two techniques is dynamic passive haptic feedback, short DPHF. The idea of this hardware-based approach is to equip proxy objects with simple actuation in order to let them adapt their passive haptic feedback properties. So for example, their shape, or in our scenario here, the internal weight distribution by using a weight shifting mechanism that is built inside the physical prop. And the second technique is haptic retargeting, a software-based approach that utilizes hand redirection to let users touch the proxy at offset grasp locations. And so the central question that is guiding our work here in this paper is whether the combination of those two techniques can better solve the challenges of similarity and collocation than the individual techniques can do alone. And in order to answer this question in our paper here, we explore 4 basic conditions and their performance in rendering the weight distribution inside a virtual stick. The first one is a baseline condition that does not employ any of the 2 rendering strategies. A second condition then only employs dynamic passive haptics by dynamically shifting a weight inside the prop to mimic different weight distributions. A third condition then only employs hand redirection that only unnoticeably redirects the user's grasp away from the proxy object's center of mass. And a fourth condition then finally combining both techniques of dynamic passive haptics and haptic retargeting by shifting the weight towards one end of the prop and at the same time redirecting the user's grasp towards the opposite side of the prop in order to enhance the physical lever distance. And so to implement these conditions in a controlled user experiment with 24 participants, we used Shifty, the weight shifting proxy that we presented in our 2017 TVCG paper. And we used the popular hand redirection technique that was introduced in 2017 by Chang and colleagues within the unnoticeability ranges that we found in our perceptual study published here at IEEE in 2019. And as a metric for assessing the performance of the different techniques in tackling the challenge of similarity, we identified the maximum conveyed virtual lever to be a suitable measure, as it is basically proportional to the number of different virtual objects that the system can provide appropriate feedback for. Concerning collocation, we identified the maximum spatial offset that can go unnoticed by users between the proxy and the virtual object along the prop's main axis to be a suitable metric, because when we grasp a virtual stick that is represented by a misaligned prop, then users might perceive an imbalance when lifting the stick, which, if not matching the visual experience, of course, can negatively influence the experience. And so by using the different rendering strategies here, we can compensate for such unintended perceptions. And so in the first user experiment, we basically compared the maximum weight shifts that we can convey. And as the video here showcases, users in this experiment repeatedly grasped the virtual stick at its center, lifted it up, and then indicated in VR where they perceive the stick center of mass to be located. And our results show that when we combine those 2 rendering techniques, we're capable of conveying a significantly greater range of weight shifts than the individual techniques alone can convey. Concerning collocation then, in a second psychophysical study, we employed an adaptive inner lift staircase method to assess how much spatial offset between the prop and the virtual object along the stick's main axis can go unnoticed, or in other words, for how much unintended weight shift as a consequence of the proxy misalignment the techniques can compensate for. And this required participants, as we see here in the screenshot, to repeatedly lift up a virtual stick that was expected to feel balanced, always grasping also at the center, and then to indicate if any imbalance was perceivable. And while misalignments of 5 centimeters were already perceivable when we do not apply any compensation in our baseline condition, misalignments of up to 10 centimeters were still unnoticeable when we used the combined rendering technique to compensate for such unintended perceptions. And so the findings of our second experiment thus validated when we combine a dynamic prop and haptic retargeting in our scenario, significantly more spatial offset between proxy and virtual object can remain unnoticed. compared to what can go unnoticed when we only use one of the techniques alone to compensate or not compensate for any of such perceptions at all. And so finally, we would like to note that our investigation here serves as a first systematic exploration of how dynamic props and haptic retargeting can be combined, and still is based, of course, on certain assumptions. For example, we only considered here offsets along the stick's main axis, and we only considered the haptic dimension of weight shift in this paper. However, in future work, we aim to explore how the benefits of combining a dynamic prop and haptic retargeting can generalize to further scenarios and also other haptic properties. And this concludes my talk. So thank you very much for listening. And I'm very happy to take any questions later in the Q&A session. Thank you.
Okay. Thank you very much, Andre, for your interesting talk. You're still sharing your screen. Okay. Thank you very much. And this brings us to the next talk, which is on wearable robotic arms for passive haptic feedback. The presentation will be given by Arata Horie, and he's a PhD student with the University of Tokyo. So Arata, please, the floor is yours.
Okay, yeah, I'm ready. Okay, thank you, Mr. Speaker, and hello, ladies and gentlemen. I am Arata Horie from Information Somatics Lab in the University of Tokyo. We would like to introduce our research encounter rooms. So at the first, I will show our work briefly. We propose the concept of the encounter type haptic presentation using a wearable robotic arm. A lightweight wearable robotic arm with an appropriately controlled end effector enables the user to perceive encounter type haptic sensation in a large space. In this presentation, we will describe the system we have developed and briefly introduce our experiment for the proof of concept. So many high-performance head-mount displays have been appeared, and the workspace has expanded to room scale. So haptic presentation has the potential to dramatically improve the PR experience, and performing haptic presentation in such a large workspace is a major challenge. On the other hand, presenting high-quality haptic sensation involves a workspace trade-off. Encounter type haptic presentation is one of them. So encounter type haptic has a long history as one of the haptic presentation methods. The method involves placing a physical end effector between virtual object and human contact point, and presenting haptic sensation through the actual contact. Traditional encounter type haptic presentation system use a grounded robotic arm. So therefore, the workspace is limited by the dimension of the robot arm. So recently, researchers proposed manipulating such a drone or balloon for application to VR. However, this has problems that they can only present low stiffness object. So overcoming this stiffness workspace trade-off is a very important issue in delivering high quality haptic experience at the room scale. So in this presentation, we propose an approach to overcome this trade-off, an encounter type haptic presentation using a wearable robotic arm. The robot arm enables active haptic presentation with high stiffness. Furthermore, by making it wearable, the presentation area can be extended to the room scale. By combining with the tracking system, we have developed a system that allows users to touch objects in a room-scale VR. And the system consists of tracker, a robotic arm, and a software in Unity. The user wears the tracker on his hand and concentrates.
I'm sorry for interrupting. It seems like your slides are not advancing.
Oh, really? Just a moment. Oh my gosh. Can you see the screen?
Not yet.
Ah, thank you.
We would like to introduce our research encountered limbs, a room scale encountered type haptic presentation using wearable robotic arms. An angular error of about 3 degrees and a stiffness of about research encountered limbs, a room scale encountered type haptic presentation. Clarify whether the results of the slant presentation using the proposed system and later experiments depended on human perception or on errors in the system. We used a grounded plate slant system to investigate the JND of perception of slant by the palm. We used constant method. As a result, it was found that people have a JND of 4.6 degrees for the vertical direction and 5.2 degrees for the horizontal direction. We conducted the first experiment using the proposed system to evaluate the performance of presenting slant in a stationary state. Participants wore the device and touched the wall in front of them without any visual cues. They answered the slant direction they touched. The directions presented were up, down, left, right, and in front without inclination. For those within slant, the conditions were 10 degrees, 20 degrees, and 30 degrees. The results of the experiment showed that in the 20 degrees and 30 degrees conditions, the system were able to render the slant direction almost completely. In the 10 degrees condition, the percentage of correct responses decreased. Considering that the static angle accuracy error of the robot arm is about 3 degrees and the JND of human tilt perception is about 5 degrees, it should be able to answer in the 10 degrees condition. We considered that the system could not completely guarantee the body swaying. Finally, we constructed a simple room in VR, and conducted an experiment in which participants were allowed to touch it freely. We prepared 2 conditions, visual stimuli only and visual stimuli plus haptic stimuli. Users explored a room in the VR for about 3 minutes in each condition, and after freely touching and experiencing the room, they answered questions about their presence in the VR. The results of the experiment showed an overall increase in presence when the participants used the encountered limbs. We can argue from these results that even if the wearing of our system itself reduces the sense of presence, the effect is still positive. We believe that the uniformity of the end effector's texture, as opposed to the multiple textures of the objects in the VR environment, may be reducing involvement and reality, and this is an issue we will address in the future. Thank you for listening.
Okay, so I understand that the next speaker is on. So the next presentation will be on tactile perceptual thresholds, and the paper will be presented by Lu Zhao. She's a PhD student with the Beijing Institute of Technology. So Lu, please go ahead.
Okay. Is my PowerPoint placed all right?
Yes, so far looks good.
Okay, I'm ready now. Okay, thank you. Hello, everybody. My name is Lu Zhao. I'm from Beijing Institute of Technology. The title of my paper is Tactile Perceptual Threshold of Electro Vibration in VR. It is a common knowledge that haptic sensations plays an important role in virtual reality. It can significantly improve users' immersive experience. High-fidelity haptic stimulation based on the understanding of the mechanism behind haptic perception has become essential for the further studies. However, when we immerse in a virtual environment, there is distorted depth perception and reduced pain perception in VR. Besides, the display of virtual scene influences our interaction behaviors. Well, what about our tactile sensitivity in VR? So the goal of our paper is to investigate human tactile sensitivity in a VR system. We estimated the tactile perceptual threshold for touch surfaces in an immersive environment based on electro vibration stimuli. Specifically, we made two psychophysical experiments to measure absolute detection thresholds, as well as frequency and amplitude discrimination thresholds for various electro vibration tactile stimuli in VR. To complete the estimation during the experiment, the participants were immersed in VR by wearing the head-mounted display, and we use a custom-designed electro vibration device to provide tactile sensations to the user's fingertip. The size of the device was 10.1 inch, and the drive signal frequency range was 10 to 1000 Hertz, and amplitude range was 0 to 255 volts. Then participants perceived the tactile sensations through the electro vibration tactile display. They were asked to explore different regions using their index finger and determine which region produced the electro vibration. After they recognized the correct region that providing the tactile stimuli, they gave their answers by pressing the corresponding button on the physical keyboard. The first experiment was conducted to investigate the baseline human sensitivity for electro vibration stimuli in VR. We measured the magnitudes of the applied voltage across in VR versus non-VR, sinusoidal versus square waves, and 5 fundamental frequencies. We implemented a two alternative forced choice paradigm. Participants explored A and B regions consecutively using the index finger and determined which region produced the electro vibration. We explored the amplitude threshold with a 1 up, 2 down adaptive staircase method. Results suggested that the absolute detection thresholds of the electro vibration tactile feedback depends on the environment and the frequency. The minimum voltage of the perceived electro vibration tactile stimuli was 15.33 volts at 120 Hertz in VR. Before and after the experiment, there were 9 and 8 participants, respectively, who thought that the tactile sensitivity was affected by the environmental condition. And after the experiment, there are 73% of participants reported that they sensed the tactile feedback more sensitivity in the non-VR environment than in the VR environment. Our second experiment tested participants' amplitude and frequency discrimination thresholds in VR. The designed tactile stimulus set consisted of 5 reference frequencies at 5 reference amplitudes. Similar to the first experiment, the amplitude and frequency discrimination thresholds were estimated using a 3 alternative forced choice paradigm, that the test stimuli provided in one region was different from the other 2 regions. And the results show there were no significant differences between the mean discrimination thresholds at 5 amplitude and frequencies, indicating that the amplitude discrimination thresholds remain constant. The mean value was 19.12%. The mean of the frequency discrimination threshold were essentially constant for amplitude, while dropping from 25% for the lower frequency group to 12% for the higher frequency group. The main effect of reference frequency on the frequency discrimination thresholds was statistically significant. In sum, our result of 2 experiments show that users' tactile perception was significantly less sensitive with a higher threshold value in the VR condition than in the non-VR condition. And the correlations between the input signals and the tactile discrimination thresholds were similar in VR and non-VR environments. Moreover, participants' self-report further supported these results that the electro vibration tactile sensation in VR system is less than the non-VR system. In a conclusion, we conducted and analyzed 2 psychophysical experiments along with an electro vibration tactile display to reveal the characteristics of tactile sensitivity in VR systems. Both the quantitative perceptual thresholds and the differences between VR and non-VR conditions were explored, and our investigation results of tactile perception could serve as useful references during the design of tactile device and haptic rendering in VR system. Thank you for your listening, and I'm glad to answer questions later.
Thank you very much, Lou, for your interesting talk. That brings us to the final talk in this session. As Lou mentioned, afterwards we will have a Q&A session. So the final talk is on unscripted retargeting, and the paper will be presented by Aldrich Clarence. So Aldrich, the floor is yours. Oh.
I'll just share my screen first.
Yes.
And hello everyone, I'm Aldrich, and today, Hello everyone, I'm Aldrich, and today I'll be presenting our paper, Unscripted Retargeting, Rich Prediction for Haptic Retargeting in Virtual Reality. Before I dive into this paper, I'll give a brief discussion about the background. Currently, when users are interacting with an object in a virtual environment, the current commercial solution relies on providing touch feedback with vibration or no feedback at all. When users receive inappropriate touch feedback, it will detract from the overall experience. Haptic retargeting is one solution to improve the haptic experience in VR by using real objects to represent multiple virtual objects. One technique of haptic retargeting is incremental body warping. As shown in the video, the technique decouples and manipulates the virtual hand from the real hand gradually to reach spatially separated virtual and physical objects. The current implementation of body warping on its own is mainly explored in a scripted manner where the users were instructed what to reach. However, a natural reach interaction should support unscripted interaction. There are 2 current solutions to support unscripted retargeting interaction. One, using additional hardware like eye tracking, or requiring user to use head gaze to select the target prior to reach. Inspired by the current problems, we envision retargeting to support unscripted natural interaction in today's VR. We propose a reach-based prediction model that predicts the user's intended target and applies retargeting to the remaining reach once a model reaches a predetermined level of confidence. We conducted a data collection process to collect the user's reaching movement. We then use this knowledge to build the prediction model, which we then evaluate its accuracy and how early it can predict the user's reaches. Finally, we evaluated with simulation to see how unscripted retargeting affects how far a physical counterpart from a virtual object can be. For the data collection, we recruited 12 participants, including 1 left-handed participant. The task of this study is to reach 24 targets placed across the tabletop, and we track the participants' head and hand movement. There were 2 instruction types where users were either informed or not on what to reach. We did this to ensure that we get the user switching movement to all the targets, but at the same time, confirming whether letting the users freely reach will affect their movement. We did preliminary visualization to better understand the user switching behavior. We discovered that different users typically have similar reaching behavior to reach the same target. This is the case for both instruction types, and so we decided to combine both ordered and random reaches to build a prediction model. Additionally, since we only have one left-handed participant and they reach differently from right-handed participants, we discarded the one left-handed participant data. We then used this switching data to build the prediction model. We decided to use long short-term memory, a type of neural network that can be trained with past user switches to predict the target of future reaches. When training the LSTM network, we need to decide the movement features to use. So we decided to develop two LSTM networks. The first one we call LSTMP, as we train it with only the hand position features, and another variant called LSTMPR, trained with both hands position and ear rotation. We then evaluated these two models with cross-validation to compare the prediction performance. Here, we show two figures with the model's prediction accuracy and confidence over time throughout the reach. The two figures contain three lines, showing mean in the middle, and the dashed lines are two standard deviations above and below the mean. We also use a green area to indicate the area where we consider as having low error and high confidence, which is equated based on our data collection and results. We discovered that both LSTM networks perform similarly, achieving high accuracy and can predict early. On average, at around 65% of the reach, the user's reach can be accurately predicted with an average error of less than 3.25 centimeters. This accuracy is considered low, as the closest neighboring target center point is 6.5 centimeters away from the real target center point. This indicates that on average, we can apply retargeting to the last 35% of the movement. We also discovered that the model's confidence of its prediction on average is higher than 85% around this time. This can be used as the predetermined threshold as to when we decide the prediction is considered as accurate enough. Additionally, we also explored whether the LSTM model can predict new user switches that the model wasn't trained on. So we created a new variant of LSTMP called LSTMPO, which is evaluated using the leave one out approach. From the results, as we can see that having data of the same user doing the reach in a training set will be beneficial to slightly improve prediction. However, it is not necessary, as the performance between both LSTMP and PO is very similar. We further compared our two variants of LSTMP and PR with other prediction models from the literature, including the nearest neighbor approach, pairing angle, and regression. LSTM performs the best in terms of accuracy and ability to do early prediction, followed by the nearest neighbor approach. And when compared to the nearest neighbor approach, at 65% of the reach, the LSTM networks perform approximately 5 times better and can predict 1.23 times earlier. We then use simulation to see how unscripted interaction affected retargeting, as in how far a physical proxy can be from the virtual object in our setup. To do this, we use the proposed range by previous work of how far a hand can be displaced without being detected. And we were able to confirm that scripted retargeting has larger space to place a physical proxy away from the virtual object due to having farther distance to apply offset. However, in our setup, this translated to only having 2 lesser physical objects to represent the entire 24 virtual objects in our setup. To summarize, our research focused on enabling unscripted interaction with retargeting. We presented the use of LSTM to predict the user switches, and this approach is beneficial as it works with today's commodity VR devices and does not add additional steps to reaching with retargeting. Initial results are encouraging to keep looking in that direction, as it's able to predict early with high accuracy over previous methods. However, further user evaluations are needed to fully validate the application of LSTM to retargeting's implementation. Thank you.
Okay. Thank you very much, Aldrich, for an interesting talk. I think this concludes the part of the presentations, which means that we will now go to the Q&A session. And people have asked a lot of questions in Discord. I encourage people to continue asking questions on the Discord channels. Yes. Okay, thank you very much. So let's start the Q&A session in the haptic session. So here's a question by Sebastian Friston for Song Chol on the floor vibration. The question is, how do you think the results would be affected by having the participants driving the car?
Yeah, that is a great question. So absolutely, I would say if the participant take the driving, then they will have a less cyber sickness. There is a similar symptoms that in real world when there is a report when the driver has a less motion sickness rather than passengers. So in our study, the main research question is if our platform can reduce the cyber sickness, we intentionally provide the participant to experience the simulator from the passenger's perspective.
Mm-hmm. Okay, thank you. There's another question for Andre, the dynamic passive haptics and haptics retargeting. The question is by Maud Marshall. Have you tried other tasks, motions where the combination could improve the weight sensation?
That's also a very good question. In fact, in this study, we did not study any other interactions. We only studied this very controlled interaction of grasping the stick. During this grasping phase, we had the hand redirection activated, and then lifting the stick and feeling its weight distribution. So people, of course, could like wiggle the object around a little bit and feel how the weight is distributed. But they then just put back the object again and estimated the internal weight distribution. So other interactions, like more complex interactions, wielding the object, hitting some user interface elements or something like that, were not tested. But I think this is just because we wanted to have some very controlled setup for this study, as we wanted to specifically show a very controlled effect. But in future work, I think that would be a great idea to study also how gains and hand redirection, also while we are grasping the object, could affect the perception of weight distribution. There could be some pseudo-haptic effects that that could even enhance this on top of the combination of dynamic prop and hand redirection. There could be added a pseudo-haptics dimension to this, I think, as well. So I think that's a really cool idea for future studies.
Mm-hmm. Okay, thank you, Andre. So here's a question for Arata. How much force can this end effector withstand from users' arms? Does it depend only on the motor specification or something else, i.e. posture of the robot arm? The question was asked by Takeru Hashimoto.
Great. Thank you for your comment. Actually, the force of the system can present is strongly related to the posture of the robot, but yeah, at most under 50 newtons. And our system evaluation shows that the stiffness over 20 newton by meters. And if we use, passive brake system at the same time, the presentable force can be significantly improved, I think.
Okay, thank you very much. So I have a question for Lu Zhao regarding the tactile perceptual thresholds. So the question is, I was wondering how the visual feedback could have affected the user's perception. Have you tried to perform some trials without visual feedback? Again, the question was asked by Maud Marshall.
Yeah, actually, we have further estimate the electro vibration threshold, detection threshold without visual feedback in the VR when they wear the head-mounted display. We provide the visual feedback and without the visual feedback, but actually the results show it didn't show the effects about the visual feedback currently. Yeah, about the perception, we think there may be something other factors that results our that influence the results.
Okay, thank you. One question for Aldrich. How large was the data sets for each user? The question was asked by Bruce Thomas.
Thanks for the question, Bruce. So we recorded 12 participants, and the total of trials that I collected was 936 trials. But for the building the prediction model itself, this translated to around having 80,000 records being trained with features like hand movement and rotation. Yeah, that's all from me. Thanks.
Okay, thank you very much. So here's another question for Songchol. You said that you cannot be sure whether vestibular stimuli are similar enough to the ones that one would experience being driven as a passenger. Do you think that you could calibrate the actual vibration level by recording it from a real route and actually modeling this route? Would your vibration plate have enough degrees of freedom to model arbitrary bouncing in the car? This question was asked by Adrian Kreskowski.
Thanks for the nice question. So actually, because of the limited length of the presentation, I couldn't say about that, but I explained it in the paper. So actually, we measured the intensity of the vibration from our platform using the data logger, and then also we compared the result when we actually drive the pickup truck on a road, and we measured the intensity from the real truck and had a comparison between them. And then because the result says that it is reasonable to accept the intensity from our platform, we just use it. But actually it cannot say we could identically reproduce the same amount of intensity during our platform, the experience. And then also the other limitation was our intensity was only delivered to the vertical direction. But in real world, the vibration could be delivered through all the ways. So that was the limitation from our platform. So that is the reason why I just say that was not identically we provide the vibration feedback.
Okay, thank you. Here's another question for Andre. If I understood correctly, you only tested for one fixed weight. Are these findings transferable to significantly lighter or heavier weights as well? This question is from Sebastian Kmentowski.
That's also a very good question, I think. That's something I didn't mention in the talk, but yes, that's right. We only tested a single fixed weight that was exactly as heavy as we originally published it in the Shifty paper for the prototype. And we also used for the hand redirection a certain maximum amount of hand redirection, because we limited the redirection to be unnoticeable. So we limited it to the degree of the perceptual threshold, so to say. And in general, I think the results are very transferable to other weights, because the underlying physical laws that we're using here are exactly the same, no matter how large or heavy the weight is. And also, no matter how far we redirect the hand, what we essentially do at the end is we have a lever distance. This is basically the distance between where we grasp the object, between our hand and the location of the center of mass. And this lever distance is increased on the one side by using the dynamic prop, and on the other hand, also further increased by hand redirection. And so it's basically independent of the weight. However, of course, if you use a weight that is too light and the shift does not result in a torque that is noticeable by a human, then you would, of course, not perceive it. But as long as you use a noticeable shift range and a noticeable torque, the technique should work for other weights as well.
Okay, thank you. Here's a question for Arata. Did the user feel the inner force through the device on the back? When the user pushes the plate, he/she might feel as if someone were pushing at the back simultaneously. I'm interested in the noticeable threshold of such force. The question comes from Yasuyuki Yanagida.
Actually, it is a very good question, and it is kind of general issue in wearable haptic system, right? So yeah, actually, the user do not feel so strong sensation because of the inner force. It is because already the user already perceives the strong pressure caused by a robot weight, and it is follows Weber-Fechner's law. The inner force sensation is not so strong compared with the hand sensation.
Mm-hmm. Okay, thank you. Here's another quick question for Lou. So is the amplitude, or is there any mechanical vibration in the display, or is it just a sensation or kind of an illusion to the user?
Illusion, you mean? Pardon? Sorry.
Is there a mechanical vibration in the display?
Yeah, it's vibration. Although it has electrical vibration, but when we touch the surface, it just feel like when we touch the traditional mechanism vibration. Yeah.
Mm-hmm. Oh, okay. Thank you.
Thank you for your question.
Another question for Aldrich. How does the system or your prediction perform when the origin of the reach is somewhere else?
Yep. So thanks for the question. That's an interesting point. Like for what we're currently trying to explore is an alternative method from the existing works that is able to support unscripted interaction. However, like for future works, there definitely needs to be like further exploration on what we can do to support like more like free reaches from different direction. And yeah, I'm also considering different factors, like instead of setting a specific target, but predict coordinate in space. Yeah, thanks.
Okay, thank you very much. So we have lots more questions. Maybe we can make one more quick round of questions, and then maybe the authors can ask the remaining questions on the Discord channels themselves directly. So another question for Songchol is, do you think if there was a motion platform, this would help? This is from Bruce Thomas.
Thank you for the nice question again. So the quick answer is yes, I would say yes, because in our platform, as I just mentioned, we just provide the stimuli through the vertical direction. But if the motion platform, some motion platform provide the stimuli to the horizontal direction as well in a proper strategy, then I would say yes, it can reduce more cyber sickness. More, yeah.
Okay, thank you very much. Another question for Andre. When we want to express various mass distributions, how should we combine HR and DPHF method? Basically, should we use DPHF and use HR to augment the parts that cannot be expressed by DPHF? The question is from Takeru Hashimoto, and maybe you can try to answer with a short answer, Andre.
Of course. Thank you, Takeru. It's a really good question, and we described that in more detail in the paper. But essentially, this is exactly how we do it. So if we have a certain shift that we want to render, then we basically just render it using the dynamic prop, using Shifty. But if this shift exceeds the shift range of the prop, then we just take the remaining part that we cannot render using the prop and add this by using hand redirection. So this is exactly how we do it.
Mm-hmm. Okay, thank you.
Thanks.
Here's another question for Arata. It's from Kenichi Ito. If the users move their arms too quickly, I think the robotic arm cannot track such movement and the users fail to touch the panel. Do you have any solution? Is there a quick answer to that question, Arata?
Okay. Thank you for your comment. And yes, exactly. Even if we can use strong motor and realize quick motion, such a quick motion of the robot is very, very dangerous. Yeah, actually, it was very tough challenge to create the safety specification defined in collaborative robotics in current specs. Fortunately, the system has two arms, so for the future plan, we can use another arm into the predicted surface.
Okay, thank you very much. One last question for Aldrich. It's from Nami Ogawa. This may be a rudimentary question, but do you need to recollect the dataset from scratch if the configuration of the targets changes?
So thanks, Nami, for the question. Regarding predicting targets in random areas, our current approach is discrete and classifies a reach to a target. In our case, the target has a preassigned position in the environment. As future work, however, it may be possible to develop a continuous approach using similar deep learning techniques, which would instead predict a touch location anywhere in the space. This would allow for a much more generalized approach for spatial layouts and reduce the need for retraining. Thank you.
Okay, thank you very much. So I think in the interest of time, we should conclude the Q&A session here. If there are any remaining questions, and there are some remaining questions on Discord, maybe the authors can go to their Discord channels and answer any remaining questions. I would like to thank the authors for their presentations and for the interesting discussion. And of course, I would also like to thank all the attendees for joining and for answering all these great questions. Thanks to everybody, and have a nice conference for the remainder of the day. Bye-bye.
Thank you.
away.
Okay, so good morning, good afternoon, good evening. So welcome to the third keynote of IEEE VR 2021. So before introducing our presenter, I would like to remind you that you can ask questions on Discord. We'll have 15 minutes for questions after the 45-minute presentation. So please feel free to ask any question on the channel dedicated to the keynote. So coming back to the keynote, so it is my great pleasure to introduce Professor Frank Steinecker. Frank is Professor for Human-Computer Interaction at the Department of Informatics at the University of Hamburg, and he received his PhD from University of Münster in 2006. And his research is driven by understanding the human perceptual, cognitive, and motor abilities and limitations in order to reform the interaction as well as the experience in computer-mediated realities. So Frank regularly serves as panelist and speaker at major events in the area of virtual reality, and is on the international program committees of various national and international conferences. So today, Frank proposed an exciting keynote about the fusion of mixed reality and artificial intelligence, and his presentation is entitled Blending or Bending Realities. So Frank, the floor is yours.
Yeah, thank you, Maud, very much for the kind introduction. I'm going to share my screen right now.
Yeah, thank you.
And Maud, please let me know if you can see and hear me. Okay, perfect.
Yeah.
So moin, everybody. Moin is, by the way, the Northern German way of greeting, and it's perfect for venues like this because you can say it in the morning, in the afternoon, and in the evening, and therefore I don't have to worry about your time zone. It's hard to express how honored I feel to give a keynote at my home conference and talk a bit about how virtual reality has bended my reality and how I think we can blend reality and virtuality for the ultimate immersive experience. So since 16 years, I haven't missed a single IEEE VR conference, and you guys can't imagine how much I miss it to see you all in person, having a face-to-face discussion with you, as well as a beer with you after this pandemic, as we have enjoyed it for so many years. As I just said, my first VR conference was in 2005, when it was held the first time in Europe, more specifically in Bonn, Germany. And Martin Goebel was the general conference chair, and he was so generous to send me some pictures and also this original t-shirt from that time. I hope you can see it, which I'm wearing for today's keynote. And one of the pioneers in our field, Dr. Frederick Brooks from the University of North Carolina in Chapel Hill, gave the keynote back then. And I feel really honored that he served as a reviewer for my habilitation a couple of years ago. So as a young PhD student, I was really overwhelmed by the immersive technology that I could see during the exhibition at this conference, by the fantastic and inspiring research presentations, and to see all the pioneers of our field in person, whose paper I've read before. So this was the conference which convinced me that I want to dedicate my professional and work life to mixed reality and three-dimensional user interfaces. And since then, I attended IEEE VR every year, and we published a couple of papers, not only at the conference, but also at co-located symposiums and workshops. And you might recognize some of these pictures here in case that you read some of our papers. I will not talk too much about the work that we already presented here at IEEE VR, but will focus a little bit more on our work, which was published elsewhere, such as in CHI and SIGGRAPH, but still, of course, mostly related to immersive technology. So indeed, IEEE VR in 2005 wasn't the first instance of this conference. In fact, the roots of this conference date back to the year 1993 during the first VR hype. The conference was held under the name Research Frontiers in Virtual Reality in San Jose, and in the same year, Virtual Reality Annual International Symposium in Seattle, Washington, and later both were fused to IEEE VR. Betty Moeller in her keynote challenged us to talk about our first VR experiences. And I'm not sure if this was a coincidence, but in the same year when the first IEEE VR conference was held back in 1993, I got in contact with VR. And I would like to give you a little bit about the context of 1993. So this was the year when Bill Clinton became the president of the United States. And it was also the year when the first smartphone, the IBM Simon Personal Communicator, was launched. And by the way, this Simon Communicator weighed half a kilo and the battery lasted only for 1 hour. Unfortunately, that was also the time when a new music style called Eurodance, which is a mixture of techno, dance, and house, swarmed Europe. And I'm not sure if Eurodance ever made it into the US charts, but it sounded like this. Before I play it, actually, I would, and if you're watching in Verbella, please prepare your avatar for a couple of seconds of dancing. So in Verbella, you can use a right click on your avatar and then choose dance or press F7. I'm not in Verbella right now, so please somebody make screenshots of some dancing avatars and send it to us via Discord. So prepare your avatar for dancing, and here we go. This was Eurodance in 1993. So that's enough for Eurodance for now. I hope you were able to dance a bit and make some pictures. So this was the time when my mind was bended the first time by VR technology. As a 16-year-old teenager, after a disco night with Eurodance music, on the next day, we went with some friends into the Cyberspace Cafe in Berlin. And this cafe featured an amusement arcade with machines from W Industry, later called Virtuality. And here I was able to play my first virtual reality game called Dactyl Nightmare. And please add a +1 if you played Dactyl Nightmare 2 in Discord. And in this game, the player was placed in a surreal world, which looked like an Escher-like checkerboard pattern. And the game featured all major features of current VR games. So it had 3D stereoscopic display, head-mounted displays with head tracking, multi-user networking, etc. And though the quality was really bad back at this time, my mind was blown away. So by playing the game, I really had the illusion that I was there in this Escher world. I really had the illusion that the dragons were flying and trying to catch me. And I really had the illusion that I'm there together with my friends. It took some years until I actually learned from Mel Slater that these illusions are called place and plausibility illusion, which compose the sense of presence, social, and co-presence. So the feeling of being there together with others. And obviously, we had made enormous advancement within the last 3 decades. And today's VR technologies can provide compelling experiences and clearly evoke a high sense of presence, social, and co-presence for our users, as illustrated here in the latest marketing video for the Microsoft Mesh platform. It's still not perfect, but it's good enough that it will never disappear, in my opinion. Indeed, Gartner evaluated virtual reality and augmented reality as technologically mature and therefore removed VR and AR from their hype cycle. You can argue about this, but more specific technologies have already entered the cycle again, such as immersive workspaces, AR cloud, or intelligent agents. I think we all agree that it will take some more years of technology advancement before we can experience the ultimate immersion and before VR and AR technology will be available as ubiquitous as smartphones today. So the question is, what can we do as long as the technology is not perfect? Well, obviously we can do engineering work and improve the technology. However, this might take years and enormous resources. And I further argue that virtual reality technology will probably never be perfect. Hence, in my keynote, I would like to take a different perspective and would like to show how imperfections of the human information processing can be exploited to bend reality in such a way that we get closer to an ultimate experience in which reality and virtuality are seamlessly blended together. And such blended spaces are nothing special. Even our own reality can be considered as a blended space, which is composed of the dichotomy of the natural and the artificial. And according to the German philosopher Bimbacher, the distinction between natural and artificial occurs at the impact level. So natural denotes everything that became without human being, and artificial, which was made by human impact. And although this distinction is central to our orientation in the real world, artificial flowers or trees planted by humans show already the blurring between the natural and the artificial. And also in our own field, computer science, is evolving into a blended space. In classical computing, data is encoded in fundamental units called bits, where each bit represents a distinctive state, which is either 1 or 0. However, we observed the shift from this classical model of computing towards other approaches, such as quantum computing. And here data is encoded in so-called quantum bits, which can represent a 1, a 0, or a coherent superposition of both states simultaneously. And with this probabilistic approach of qubits, the area between the 1 and the 0 can also be considered as a continuum. So in my keynote, I would like to focus on 3 fields in the area of AI, mixed reality, and robotics, and show how they blend together. So let's start with mixed reality. As you know, mixed reality is a combination of real and artificial environments presented via some immersive technology. And 3 years ago, I had the honor to meet Ivan Sutherland, who is one of the grandfathers of immersive VR technologies. And I think most of you are aware of his famous essay from 1965, The Ultimate Display. And in this essay, he speculated what an ultimate immersive experience would look like. And he wrote that, of course, the ultimate display would be a room within which the computer can control the existence of matter. And he gave some examples. So he said a chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining. And a bullet displayed in such a room would be fatal. But he also wrote that with appropriate programming, such a display could literally be the wonderland into which Alice walked. So the ultimate display would be a computer-mediated reality, which would get indistinguishable from the real world. And this notion of a virtual reality environment is often used in science fiction to question whether we truly know if our perceptions are real or not. And movies like The Matrix, directed by the Wachowski sibling, is a prominent example of this perceptual ambiguity. And actually, the notion that our real world is only computer-generated simulation has been shown the first time in the German science fiction movie World on Wire, directed by Rainer Fassbinder in 1973. And already 5 years before this vision has been shown in this movie, Ivan Sutherland was able to build the first prototype of such an ultimate display, as shown in this video here. The linkage and cables on top of the users, sometimes denoted as the sword of Damocles, are used for mechanical tracking. And they are combined with an optical see-through display, which allows seeing the real world and overlaying it with virtual content, as illustrated here with such a wireframe cube. And though the ultimate display is, say, described a fully immersive experience, the first display built by Ivan Sutherland and his team was actually an AR display, which allows to blend together virtual and real content. And for such mixed reality environments, Paul Milgram introduced the reality-virtuality continuum. So if we consider real-world objects on the left side, such as these two broken vases, and virtual objects on the right side, like a vase and a flower, there are 3 different ways of getting from one side to the other. First, we can augment real-world objects, for instance, by adding virtual flowers in the real vases, as described in Milgram's mixed reality continuum. But we can also diminish objects, for example, by removing the broken parts of this vase, resulting in diminished reality or diminished virtuality, depending again if we remove real or virtual objects. And finally, we can modulate real-world objects by changing the appearance, but without actually adding or removing any objects. And this model is a finer description of how to get from reality and virtuality or vice versa by augmenting, modulation, and diminishing objects. To implement such a space, which allows to augment, diminish, and modulate reality and virtuality, my postdoc Susanne Schmidt built a cave with movable projectors and depth sensors, which allow to superimpose 3D physical objects. And here's a short video of how this blended space could look like in a museum context. So what you see here is a physical dinosaur skeleton, which can be superimposed with augmented reality content, as illustrated here. So in this typical augmented reality case, for instance, you can add additional information such as annotations or highlight certain parts of the dinosaur. In a second or so, you will see the alternative approach of augmenting by using the modulation. In this case, we don't add like additional objects to the scene, but just modulate the physical objects in the scene, like, for example, adding a skin to this physical dinosaur. And finally, we will have also the diminished reality situation in which the background, which is displayed on the cave walls, will also be projected on the skeleton so that the skeleton, the physical object, seems to disappear. And the focus is here on the background. So this is one way how you can build a mixed reality space. And of course, you can use other technologies to provide this ability of augmentation, modulation, and diminishment. However, these setups still lack more dynamic scenarios in which we have seamless transition and interactions between virtual and real objects. And let's reconsider Ivan Sutherland's vision of the ultimate display to formulate some visions for such a blended space. So we wrote that a chair displayed in such a room would be good enough to sit in. So that means that in one moment, a chair could be added to the scene or modulated, and I can actually sit on the chair. But in the next moment, it can be diminished and I can't sit on it anymore. And we will call this characteristic the reality-virtuality seamlessness. Next, he said handcuffs displayed in such a room could be confining, and we will refer the ability of real and virtual objects to interact with each other as reality-virtuality interactivity. And finally, he wrote a bullet displayed in such a room would be fatal, so virtual objects can transform from virtual to real or vice versa, which we refer as reality-virtuality transformability. And this brings us to the definition of a reality space as a reality virtuality environment with one or more real as well as virtual objects and actors which support transformability, interactivity, and seamlessness. And still today, we neither have perfect mixed reality nor perfect blended spaces, but I will argue that those environment doesn't have to be perfect. According to the philosopher Horowitz, perfection itself is imperfection. And more precisely, Lucilio Vanini formulated the greatest perfection is imperfection. So the idea is, though we can't build perfect ultimate blended spaces today, at least we can exploit human imperfection in the human information process and some illusions to make people believe that we actually have an ultimate blended space. So let's have a look at the perception action loop in the human information process, which we would like to exploit. We interact, or when we interact with the world, multisensory information is processed in a bottom-up way, for example, by processing optic flow. Now, cognition interprets the multisensory cues, but at the same time also affects perception based on prior experiences, for example, and influences, therefore, perception in a top-down or hypothesis-driven way. Then cognition guides motor action, but again, at the same time, bottom-up revision regulates our actions. And finally, motor comments are initiated, which affect the environment. So we move, for example, or change our view to the environment. And finally, we can observe the updated internal and external sensory feedback. With mixed reality technology, the motor comments can now be mapped to the environment, in particular the virtual environment, for example, by changing our virtual view, by moving the head or grabbing some virtual objects with our hands. And if we do so at the same time when the efference motor comment is sent to the muscles, a copy is used in a forward model to predict the sensory feedback. And then a comparator compares the observed feedback with the predicted feedback. And typically there's always some small discrepancy between the predicted and observed feedback, even in the real world, but in particular in mixed reality due to latency, tracking errors, inaccuracy, or imprecision of the sensors, etc. If the discrepancy is small enough, people will not notice and simply adapt their motor control, as long as the multisensory integration will result in a plausible observed feedback. However, typically in virtual reality, different senses are in conflict. So for instance, the visual, vestibular, and proprioceptive sensory signals are in conflict when visual stimuli is presented to a stationary user, or if we use some teleportation techniques, but also due to tracking errors or latency, which will all lead to these small inconsistencies. There are essentially two models which describe how stimuli from the different senses can be combined. In the top one here, in the maximum likelihood estimation, each stimuli from the different senses is weighted in the cue integration process. And the weight typically specifies the reliability of the sense, or in the case of the second one, the Bayesian decision theory, the probability of a percept. Typically, vision gets a high weight and often dominates, for example, vestibular and proprioceptive information. And the reason why vision gets usually a high weight is that most of the information we typically perceive during our daily life is based on the visual channel. And in this visualization here, you see how much information pours in our senses. And the sense of sight, as you can see here, is the fastest. It has the bandwidth of a gigabit Ethernet, which is more than the bandwidth of all other senses combined. And I would like to draw your attention, I'm not sure if you can see this, the white square at the very bottom of this graph. So this small fraction is about 0.7%, and it represents all the perceived information that we are actually aware of. So a lot of the information is actually filtered out or not selected for further processing and does therefore not reach our conscious level in the perception action loop. And I would like to show you two examples on how this imperfection of our human information system can be exploited. The first example is derived from head-mounted display design. So the visual acuity of the human eyes is about 0.3 arc minutes. And if you want to build a head-mounted display, which provides the same field of view and resolution of the human eye, you would have to provide approximately 576 megapixels for 180 degrees field of view. And if you assign now 3 bytes per pixel, you will end up with 1.5 gigabyte per frame. Even if you think about the fastest HDMI cables that we have nowadays, that means we would only be able to display a maximum of 5 to 10 frames or so. So that's not possible today. However, there's the good thing. If we focus our eyes on certain objects in the environments, we only perceive a sharp image at that spot, which is typically very small around our retina, called the foveal region. This fovea only corresponds to approximately 2 degrees of our visual field. And to render a sharp, high-resolution image in this small region would only require 7 megapixels. And vision is really blurred in the periphery and only would require an additional 1 megapixel. So in total, we would only need 8 megapixels instead of the 576. But it would require exactly to know where the user is looking at. However, though the human visual acuity is in the periphery is rather low, humans are sensitive to notice, for example, blur or contrast changes in the periphery, as shown by David Lübke's group at NVIDIA, who just received the IEEE and the TVCG VR Technical Achievement Award this year. However, here comes artificial intelligence into play. So colleagues from Facebook Research have shown that you can apply convolutional neural networks, in particular GANs, to reconstruct plausible peripheral videos only from a fraction of the pixels transmitted for each frame, which can further decrease the required pixel to only 10%, but still provide a very plausible peripheral image. Next, I would like to show you another example which shows how information is processed. Here, I would like you to solve a murder crime. I want you to carefully watch the following scene.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
That's right, madam.
It's just a matter of observation. The real question is how...
So he is asking the question, how observant were you? And here is an image showing the start sequence of this movie. And on the lower right image, you see the end sequence of the clip. And probably some of you might have known this video before, and some of you might have observed some changes. For example, a change in the detective's coat. Others might have observed that the flower on the table has changed. However, I guess none of you have perceived all the 20 changes which have occurred in this very short video clip. And here's another clip showing the same scene from a different perspective.
Action. Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest
So the inability
Lady
of
Smythe.
humans to detect such changes which occur outside his or her view is called change or intentional blindness. And these examples show how limitation and imperfection of the human information system limits the amount of information that needs to be processed. And let's have a closer look at the different steps. So first, perceptual filtering, as we have seen with visual blur in the periphery, but it can also be observed for other senses, such as the audio sense. For example, when you think about masking sounds as used in MP3, reduces the amount of information which is required for further processing. Next, there is selective attention, as seen in the change or intentional blindness, which again can also be observed in other senses. For example, if you think about the cocktail party effect, in which you can listen, for example, to somebody and decrease the perceived background noise. And finally, we have motor adaptation, which allows us to quickly react and adapt our motions to small inconsistency or discrepancies in the sensory discrepancy comparator, which are not noticeable by our perceptual system. And I would like to give you some examples on how these imperfections can be used to improve experiences in blended reality systems. So let's start with motor adaptation. Let's reconsider the last sentence of Ivan Sutherland's essay. He wrote the wonderland into which Alice walked. So that means that we should be able as users to explore a virtual environment in the most natural way. And this is not by using a game controller, a keyboard, or a mouse, but by using real walking. And to implement real walking in virtual reality is actually rather easy. You just track the movements of the user one-to-one and map them to corresponding movements of the virtual camera. However, the problem, as most of you are aware of, is that the real environment is typically smaller than the virtual environment. And typically users are not aware of their real world physical boundaries because they wear a head-mounted display and are immersed, for example, in a virtual environment showing a building or a spaceship. And here's a video which I think Evan Zuma sent me from YouTube, showing a user who really perceives a high sense of place and plausibility illusion with a head-mounted display, and she forgets about her real-world surroundings.
You almost don't get
So these things really happen, in particular with improving technology, which even evokes higher sense of presence. And my group has now worked almost 1.5 decades to solve this issue by using a technique called redirected walking, which was originally proposed and introduced by Sharif Razak from the University of North Carolina and Chapel Hill under supervision of Frederick Brooks and Mary Whitten, another pioneer who just received the VR Career Award 3 days ago. And the main idea is illustrated here. So assume you have a user in a real world, and once the user dons a head-mounted display, there is some virtual objects here, such as this virtual chair or virtual door. If we can predict that the user wants to walk towards some virtual object, such as this chair, while the user is approaching this object, we can slightly rotate, for example, the environment around the user in such a way that the user has to walk on a curved real path in the real world, whereas he or she believed to have walked on a virtual path in the virtual world. And by doing so, we can also shift the position of certain objects. So in this case, now the virtual chair on which the user could not sit initially has now transitioned itself to a physical chair by using the physical prop of the real chair. And so the user could actually sit on this chair by using passive haptics. In recent years, we and other colleagues have identified detection thresholds in psychophysical experiments, for example, for such curvature gains. And we found that approximately a radius of 20 meters would be required in order to guide you on a circular path so that you're not aware that you're actually getting manipulated. And it's really interesting to see that with improving technology from year to year, the required radius that you need to guide users on a circular arc decreases, which shows that with improved head-mounted display technology, the weight assigned to the visual sense in the multisensory integration process is increased. However, we still need a rather large area of approximately 5 times 5 meters. However, in recent years, imperfects in the human information process have been used to further improve redirected walking techniques. In particular, we can use perceptual filtering. And the idea is illustrated here. When we explore the world with our eyes, we fixate, we blink, and we perform saccades. Detection thresholds so far were mostly focused on constant manipulation and applied to the scene while the user were fixating some objects in the VE, such as a target to which they should walk. However, we also perform blinks and saccades, and we do this quite regularly, about 20 times or 40 times for blinks and saccades per minute. And the interesting thing is that during these very short interruptions of approximately 80 to 300 milliseconds, and also a little bit before and afterwards, vision is suppressed, the visual input is suppressed. So we are literally blind approximately 10% of the time under normal circumstances. And of course, we can use these saccades and blinks. And here's work of my former postdoc, Eike Langbeen, who performed psychophysical experiments to identify how much camera manipulation is not noticeable. And he found that approximately 4 to 9 centimeters translations and 2 to 5 degrees of rotations in any direction can be added without users noticing during a blink. And this can be now combined, of course, with other redirected walking techniques. And here you see the user walking through a spaceship to which we apply already some curvature or bending gains, to be more precise here. And we can add this extra 4 to 5 degrees of rotation whenever the user performs a blink, as illustrated here in the video. Visual suppression can also be exploited for other manipulations, such, for example, hand redirection. And here's a video of our cooperation partner from the University of Saarbrücken. Again, during an eye blink, the virtual hand is shifted away from the actual hand position. So the real hand is displayed here in green just for illustration, and you see that it's slightly redirected during the movement, and during the blink, there is an additional offset. And Andre Zenner will present this paper in the afternoon. In order to fully exploit visual suppression during blinks and saccades, we need to be fast because those are really rapid eye movements and they last only for a couple of milliseconds. Hence, forecasting eye blinks and saccades can be crucial because it just gives us more time to perform the actual manipulation. And my PhD student, Tim Rolf, currently works on a CNN, which predicts eye movements approximately 100 milliseconds into the future. And as illustrated here in this diagram, this model takes for each frame the image, optic flow information, a depth image, as well as head and gaze information, and as an input, and it can then generate at the bottom right a fixation pool of potential locations where the user will gaze with corresponding probability assigned to them. And this works already pretty good as illustrated in this video here. So on the right video, you see that red corresponds to the actual eye location, green is the prediction, and blue is the baseline, which is the gaze point 100 milliseconds ago, if we want to predict the new gaze position 100 milliseconds in the future. We are currently a little bit better than the state of the art in predicting gaze, but still not optimal for predicting saccades and blinks. Therefore, we currently exploit reinforcement learning and negative rewards for example, missed blinks and saccades. And one of the essential ideas is here that in case we can actually predict that the chances for a certain saccade or blink are very high, we can evoke such eye movements, for example, by using some manipulation in the periphery, like in illumination, and thereby attracting the attention of the user and forcing a saccade or blink, which can then be used to change the scene. Next, I would like to show you how selective attention, such as inattentional blindness, can be used. And this is clearly inspired by work of Evan Zuma Rosenberg from the University of Minnesota, who used the concept of change blindness and impossible spaces to change the layout of the virtual environment in such a way that it fits the tracking space for redirected walking without users noticing. And here's an example of a user in a spaceship who grabs a virtual sphere, which is represented in the real world by a physical sphere. And this is similar to the work introduced by Love Kohli, also from UNC in Chapel Hill. Here we combine passive haptic feedback of this physical sphere and redirected walking, but we combine it also here with impossible spaces, because as you have seen, for the user, she was entering a different room and saw a different table, but in the real world, it was the same table and the same sphere, of course. And here's another video showing the combination of curvature and bending gains and impossible spaces. And these approaches are all combined by Curvature Games, which is a startup for location-based virtual reality experiences, and which was founded by my former postdoc, Eike Langbeen. So next, let's have a look at artificial intelligence. AI is defined as human intelligence simulated by machines. And this is a very important distinction. Its only intelligence is to simulate the human intelligence. And one of the pioneers in this field, Alan Turing, proposed a behavioristic stance to evaluate if a machine is actually intelligent or not. So he asked the questions if machines can do what humans do. And therefore, he proposed a Turing test in which a human observer, which is C in this figure, is engaged in a conversation by using text chat only with two hidden agents. One of them is a real human, B in this case, and the other one is an AI program. Both are hidden to the user, and they try to appear convincingly human. And if the observer thinks that the AI program is a real human, the AI program passes the Turing test. And while the Turing test was focused on text-based communication only, today's AI advancement, in particular in the area of deep fakes, will probably also allow to display audio-visual communication partners, which will soon get indistinguishable from the real world. And here's a video which was made by our cooperation partners of the University of Applied Science in Düsseldorf, who have used my input video on the left side. Hi, everybody. My name is Frank Steinecke. I'm a professor for human-computer interaction at the Department. And so he used this video and combined it with discrete overdub technologies for reproducing my sound, and also the lip sync expert technique by Prajwal and colleagues to generate a quite compelling deepfake of myself, as shown here.
Welcome everybody to my keynote of the International Conference on Virtual Reality.
Still not
and
perfect.
Three-dimensional
and
user
we are
interfaces.
a couple of years before we will have really deep fakes, which will be completely indistinguishable, also not detectable by machine algorithms. We will also see more and more AI methods for virtual reality and virtual agents, for example, when interacting with such intelligent virtual agents. And here's an example from our group, in which we used a Unity 3D model, which we combined with IBM Watson to process real-world information via sensors such as cameras and microphones. And this agent is able to process speech, gestures, but also other information stored in databases.
Hello.
Hello, how can I help you?
Tell me about HoloBalance.
In the HoloBalance project, we utilize holograms for personalized virtual coaching of elderly people with balance disorders. I can show you some project videos if you like. Are you interested in one of them?
The second one looks interesting.
So you see this agent is able to
here we go.
simulate human intelligence quite realistically, but still not perfect. And as a matter of fact, AI must not be perfect to imitate human behavior. Human behavior is not only intelligent, but includes also some unintelligent, imperfect behavior, which must be simulated by a machine to pass the Turing test. And here's one example of Google Duplex, which makes computer-generated phone calls for you. So in this example, you will hear Google Duplex making an appointment for a client.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second.
And it's really funny to see how it takes 1 or 2 seconds until the audience started to laugh at the video, because the AR started to mimic some imperfect behavior, such as stuttering or delay sounds. And it took some time until people got it in the audience. And we are also currently exploring how to include some of these imperfect behaviors and appearances into intelligent virtual agents. And here's one example, again, by my postdoc Susanne, in which she also visually added imperfections. For example, you see here this blemished skin and birthmarks to the visual appearance. However, please also listen to the video.
Hi, Louise. Have you seen Frank today?
So you might have seen after Susanne asked this agent if she has seen me, her eyes were going up and to the right, which corresponds to visually remembering. So this would suggest that this agent had to think about the correct answer, which of course in AI does not necessarily has to. There was also some stutter and delay sounds such as which also suggests some uncertainty in her answer. And finally, she was rather imprecise by stating that it was around noon. So something that we would do as humans, but probably not as agents. So, and we believe that these imperfections can be used to improve natural communication, but also trust and social presence when interacting with intelligent virtual agents. And using such imperfect intelligent virtual agents might also be an interesting approach towards explainable and transparent AI, since uncertainty of the results, for example, of a machine learning algorithm, could be shown by an IVA in a more natural way. So lastly, I would like to briefly talk about the Internet of Robotic Things, which brings together autonomous robotic systems with the Internet of Things. And here I just would like to show you some examples of videos of our group. So this is my former PhD student, Dennis, who used a Microsoft HoloLens and speech and gestures to interact with a shadow hand, a robotic hand. And you can see in the mixed reality display that we use a digital twin of this robotic arm with which the user can interact in a multimodal way before the actual robot is performing the actions. Here's another example showing the combination of mixed reality and robotic things such as drones. So in this case, my PhD student, Julia, is presenting her work here, in which she used a game controller to interact, for example, and steer and control a drone. And she has also presented her work here on augmented reality on Monday at the IEEE VR conference. And here's another example of providing visual feedback about robots in order to prevent collisions between humans and robots. So it's the idea of showing an embodiment of robotic things. And the idea is to show a humanoid representation of such robotic things. And the idea is to provide them with this humanoid representation to increase the naturalness, for example, in order to prevent a collision between a vacuum robot, an autonomous car, or any other robotic thing. And finally, I would like to show you how we can blend this all together. So AI, mixed reality, and the Internet of Robotic Things into a blended reality space. So in this video, you see a combination of redirected touching, which we have seen earlier, with variable actuators in a mixed reality setup, which support proprioceptive, tactile, and pseudohaptic cues. So this device, for example, and there are many of those 3D printed variable devices also presented here at this conference, allows to provide vibrotactile and tapping feedback by using the piezo actuations, and it also provides proprioceptive feedback by electric muscle stimulation and tendon electric stimulation on the skin surface, so simulating both sensory and motor nerves. And this is just a video of how this can be combined. And again, we have a multi-sensory integration process, which is not perfect for the individual stimuli, but results in a very holistic, realistic touch experience if combined in a multi-sensory way. And the last example I would like to show today is, again, a blending of intelligent virtual agents, Internet of Robotic Things, and mixed reality. And this is work which was done together with Gerd Bruder from the University of Central Florida, who has also brought a lot of inspiration from the work by Greg Welch's group. So the work in the video here shows physical, chemical, reality, virtuality interaction and combines a robotic golf ball with thermochromatic ink so that the agent can actually interact with the robotic ball and can also write on real paper. And here's a video illustrating this idea.
The first interaction is based on a robotic golf ball. Through a weight shift inside the outer shell, the ball can move with 3 degrees of freedom with a maximum speed of 1 meter per second. We designed a user study within a cave that simulated a mini-golf match between the participant and a blended agent. The animations of the blended agent were synchronized with the movements of the robotic ball, resulting in the illusion of the agent hitting the ball. The agent played the ball along a predefined path into the hole. Afterwards, the agent headed back to a table at the entrance of the mini-golf course to record her score using a prepared scorecard. In this context, we demonstrated our second virtual physical interaction, persistent writing on a sheet of paper using a thermal table. The table is a custom-built device to activate thermochromic ink on a sheet of paper via temperature variation. Initially, the blended agent writes a projected score onto the sheet of paper. In the course of the mini-golf match, the temperature is switched from high to low, and the previously transparent ink turns black. Therefore, when the user takes the scorecard outside of the mixed reality environment, the score is still visible as it is physically written. Participants of the study described the experience as fascinating, more realistic, and memorable. Further information can be found in the paper.
Okay, so in the last 5 minutes or so of my keynote, I would like to talk a little bit about the future and how I think how these blended spaces and realities might evolve. At least there's one thing that Corona taught us, which is exponential growth. In computer science, we deal with exponential growth since the very beginning of our own discipline. And in the last century or so, we have seen exponential growth most prominently in the Moore's law context, but also before Moore's law, when it was only about transistors or vacuum tubes or relays, we have seen this exponential advancements. And here are just a couple of the examples which I addressed today in my keynote with Alan Turing and Ivan Sutherland, also my first VR experiences. And this is more or less where we are today. And the good thing about exponential advancements is that you can easily predict how this exponential curve will continue. And as I just mentioned, from Moore's law, we know that approximately every 1.5 years, our computing performance will double. So that means, roughly speaking, that the bandwidth, the storage, processing power, maybe resolution, will approximately double every 18 months or 2 years or so. So we can have like a quick look into the future and see how this technology might evolve within the next 15 years. So if we know the performance doubles every 1.5 years, we know that in 1.5 years from now, our machines will be double as good as they are now. It also means that in 3 years from now, the machines will be 4 times better. And 4.5 years in the future, they will be 8 times better. And if you continue to do so for the next 15 years, you will quickly realize that in 15 years, we will have technology which is 1,000 times better than the technology that we have nowadays. And that's a really interesting question to think about. What kind of problems can we solve if our technology is 1,000 times better than the technology that we have today? And there is one specific problem which will be certainly solved within this time frame, and it's called the graphics Turing test. The graphics Turing test is a variant of the Turing test, which we just discussed earlier during my talk. But the goal is here to render virtual objects in real time, which gets indistinguishable from the real world. So think about a computer game, which you cannot, in which you cannot tell if the content has been video captured or rendered by a computer. Indeed, this is possible already today, but here you have to think about real-time graphics. Yeah? So we don't talk about Hollywood blockbusters, but by computer games or virtual reality environments, and they should look like a Hollywood blockbuster. And in 2006, McWeigan and colleagues estimated that this would approximately require 1 petaflop so that we are able to render photorealistic computer graphics in real time. With current GPU and CPU performance, we are approximately in the range of 5 to 10 teraflops. So we just need to be approximately 100 or 200 times better to solve the Turing test. And that means that within the next 5 to 10 years, actually, we will be able to reach this 1 petaflop and render virtual environments which are indistinguishable from the real world in our mixed reality environments. And here's just one example what that would mean, being 1,000 times better, for example, in rendering. So when I finished my high school in 1996, I also spent some time playing computer games. And back in the time, Tomb Raider was kind of the one of the most amazing games. And back in 1996, Lara Croft's rendering in real time looked like this. Then, approximately 1.5 decades later, Lara Croft was already looking like this. And another 3 years later, in 2016, Lara Croft was looking like this. And if you just think about being 1,000 times better in real time, like this rendering, it really gets clear that in the future we will be able to render virtual environments which get indistinguishable from the real world, which we display in our mixed reality technologies. And of course, there's a lot of ethical questions and societal challenges which come to this, as we already observe in deepfakes, for example. But also the form factor of our head-mounted displays will evolve, and we'll observe new form factors such as contact lenses. And most big players in the field have already filed their patents for some smart contact lens or smart glasses. And so we will also probably soon observe how the era of smartphone will come to an end and might be replaced by smart glasses. And it's really interesting to see that we already observe this shift. So here are the global smartphone shipments from the last 1.5 decades. And for the first time in the last 2 decades, we can observe that the global smartphone shipments decrease in the last 1 or 2 years. So hence, I believe that augmented reality and mixed reality both have enormous potential to enable more natural and human-like communication and interaction with computers and computer-mediated interactions between humans, for example, as forced now by the COVID pandemic over distance. AI has the potential to take over a lot of tasks from us, like autonomous driving, decision-making, and robotics. But at the same time, it will give us more freedom and time to focus on the essential aspects of human being, since empathy, emotions, creativity can always only be simulated by machines. And I'm really looking forward that our community is working on blending our reality with the virtuality and human intelligence with artificial intelligence. Before I finish, I would like to thank so many people here in the audience. And here I just listed those people outside my own group with which I co-authored papers and which are active members of our community. So I'm sure that many of those are here in the audience. Sorry if I missed anybody, but this is already a very impressive list of peers, which underlines also how well we can work together in our community, which are really acknowledged over the last 2 decades or so. And finally, I would like to thank and close with a thanks to my group, which of course did all the work which I presented here. So first, thanks to all of them, and also thanks to you for listening. Thanks.
More, the stage is yours.
Okay, so thank you very much, Frank, for this awesome presentation. So I guess we got a lot of dancing screenshot on Discord. So
Perfect.
yeah, so this was a success. I don't know. We will check on Virbela after the presentation. So for your information, so Frank will be in Virbela after the presentation, so you can discuss. So we have some questions. So I will start with a question from the general chair, Joachim. So Frank, do you think that Milgram's continuum still provide a good model of the application we can do?
Yeah, absolutely. So the model which we provided, which is a little bit more finer description, is not a replacement for the Milgram continuum. And actually, you could argue that the mixed reality continuum by Paul Milgram includes the modulation and also includes the diminishment, because if you want to diminish an object, what you do is you augment it, for example, with the information which is in the background. So that's an augmentation case. But at least conceptually, I think these are different things, like adding virtual objects or changing the appearance of real-world objects and also diminishing other objects. It just helps me to think about what we are actually doing. But still, the mixed reality continuum by Milgram is very valid and incorporates all the aspects which I mentioned.
Yeah, okay, thanks. And then still in the general question, so we have a question from Kiyoshi. So Frank, do you think that blending reality techniques for the BR native, so I think the blending reality native generation in 20, 30 years in the future will or should be different from the current ones, and how?
Yeah, so obviously, I mean, a big problem is still the hardware limitations that we have when it comes to head-mounted display, which are still bulky and heavy, much better than the ones that we had like 20 or 30 years ago, but still, I mean, if you think about how graphics evolved and compare it to how the HMDs evolved, there's like a gap in between. However, I'm really sure that with this new era of smart glasses, which is already starting, and we see new head-mounted display coming out like literally every month or so, we will soon be within the next 10 years or so really having head-mounted display which provide a visual quality maybe comparable to what we see on a desktop, and really in a form factor which is more or less like sunglasses or regular glasses. It will probably take a little bit longer until we really reach contact lenses with such a resolution and image quality. But I think at this there will be this tipping point at which the quality will be so good that it will just replace everything that we had before, like smartphones and something like this. And we are not there yet, but the technology, as I mentioned, is good enough that it will not disappear. So there are many applications in business, in education and training in which VR is now more or less a standard in usage, but it's still not that ubiquitous that we all believe it's going to be someday if we just walk around with our glasses and get all the informations, not on the small smartphone screen, but we need to take out of our pocket, but just in our field of view, superimposing the real world.
Okay, so Kiyoshi had an information when you were speaking. So he meant that those experience from childhood will perceive blending reality differently. I think the youngest person that we have like as kids now will perceive this differently in 20, 30 years. Do you think this is...
It's an interesting it's an interesting thing to think about, how a child, if it grows up, maybe already with 2 years or 3 years wearing some glasses, which might be used, for example, to project the mommy and daddy if they are traveling so that they can interact remotely with their parents. And if this rendering is as good as is the real person would be, of course, it's really challenging to think what this will do. And so from an evolutionary perspective, I think it's also interesting to consider that the world in which we have been born for the last 200,000 years was identical to the world that we left when we died. And only since the Industrial Revolution, so since 100 years, this is not valid anymore. Yeah, and of course, our brains have never actually learned in this 200,000 years of evolution to cope with such dramatic changes during our lifetime. Yeah, and I think it's a really fascinating ethical and social question, how we deal with this new era of combining reality and virtuality, in which you can't tell what's real and what's virtual anymore. And we have these debates already today if it comes to deepfake and fake news. And those debates will probably even be stronger if the virtual objects are just surrounding us and we don't know if they are real or virtual.
Yeah. Yeah, and do you think, like in terms of ethics, that we should, like in the community, maybe handle some ethical questions, I guess, like regarding all this new evolution, like fake avatars, etc. Do you think that is something that we should handle like very soon, Or...
I mean, we have ethics since a couple of years also in the call for papers. So that's at least something that we as a community acknowledge. However, I still believe that we have way too less experts from philosophy or ethics in our community. So in our department at the University of Hamburg, which is really nice, we have an ethic expert, a philosopher in psychology in the Department of Informatics. She's not an expert in virtual reality, but an expert in big data and AI. And we really acknowledge the discussion that we can have really with an expert on the field and not just by thinking as a computer scientist about what kind of ethical questions we should have. Of course, we should ask us these questions, but I think we also need experts from the other sides who help us also to addressing these ethical, moral, and social questions.
Yeah. I guess this was related to the next question, which is like, do you think that switching is from Katarina? Do you think that reaching a level of rendering 1,000 times better than what we have currently can be kind of dangerous somehow? I would say instead of like eating some walls, but there's some other.
Yeah, I mean, I think in particular these questions: should I always know if the things that I'm seeing are real or not? And if I say real or not, I mean computer generated or virtual. And this is actually a question which we should ask ourselves already today. If you just buy any magazine, you know that the male or female person displayed on the magazine are photoshopped. There are certain things change, but we are not informed about this officially. So we see something and we just expect it's real. And of course, this is a danger for the younger generation if they grow up with this information. And this applies, of course, also to virtual reality. I assume at one point, if virtual reality is getting more ubiquitous, we will have to answer these questions, which are already there now, but which are not so maybe perceived as dangerous or critical as they might be perceived once we don't have like a printed piece of paper or something on the screen, but something which is kind of together with us in our surrounding, and in the worst case also interacting with our physical surrounding.
Yeah. And there is a question still relating to this evolution. So Michael is asking if processing gets like 1,000 times faster, does HCI needs to evolve in the similar speed? Should we evolve in a similar speed that?
That's I think I have in my lectures at the very beginning in my HCI course always one lecture which shows this exponential advancements of technology and at the same time the evolvement of humankind, which is more or less a flat line. So unfortunately, or maybe also for good sake, the humans haven't really evolved exponentially in their abilities, which is quite surprising, because if you think about if we before we get born, we actually develop ourselves from cell to cell in an exponential way, but then at some point it moves to a linear, and also our entire thinking of the world is pretty linear, and we are really bad in thinking exponentially, as you have seen with the corona crisis around the world, and many people not understanding the effects of exponential growth. So I think for now, and probably for the next decades or so, we have to live with this constant evolvement and maybe just a very slight linear increase of our abilities. But of course, at some point, and this is something which you typically see in dystopic science fiction movies when it comes to like this mixed intelligence, which is not only about externalization of AI, so I'm using a computer to help me, but kind of internal usage of AI, like in brain-computer interfaces in which you want to kind of bring certain knowledge of the machine towards your own neurons. But I'm pretty sure that this will only be possible once I'm not there anymore, probably. So that's not something that we will expect in the next 10 or 20 years. But this might be a case in which you can actually also evolve probably much faster as a human being in terms of your ability to do something. But I would always argue this is not something that we should aim for or address for, but we can use AI in collaboration as an external thing that we use and not as an internal technology, as long as we don't necessarily need it. Like if you have like handicapped persons or something like this, in which you can actually help certain areas in the brain, for example, to perform motor tasks, that's a different thing. But I think for a healthy person, we shouldn't focus too much on bringing AI into our brain.
Yeah. Okay, so I think we have time for a last question, maybe still on the human perception side. So a question from Rick. So the technique you have discussed and presented, you focus on manipulating the world to match the expectation of a human user. Could we productively take advantage of the alternative approach that is manipulating the human, or specifically their expectations, such as the world that exists already match what's
Yeah, that's an interesting thing to not only manipulate the virtual environment, but also the user. And of course, in some cases, we do this by priming users, for example, regarding their expectations regarding a virtual environment, which is, for example, often used in social psychology, for example, to get different answers. I haven't thought too much about this alternative approach, but I'm happy to discuss it with Rick in the Verbella room in a couple of minutes.
Yeah. So okay. So I think like we are done with this question of answer. So we have a lot of other questions on Discord. I think like Frank will have a look after the keynote and could answer, or directly in Verbella. You can discuss with Frank. So Frank, I would like to thank you again for this very, very nice presentation. And I think we have an announcement from the CDI contest. Is that correct?
Yes, exactly. Hello, everyone. Thank you, Maud. Thank you, Frank, for this great keynote. I will quickly share my screen. So this is a quick announcement. I hope you can see for the 3DUI contest that is taking place at 1400 today. And on behalf of Luciano, Jaume, and myself, who chaired the contest, I would like to present some information and a fast forward of the projects you can see today. So there were 25 projects submitted this year to the contest. We accepted 17 of them, and the criteria of this were that the topics should be a fit to the theme this year, which was challenging pandemics. So in the context of COVID-19, we choose this theme, and the projects had to be innovative. They had to provide high usability, be aesthetically pleasing and enjoyable and thought-provoking. So the scoring will also comprise a final winner. So a third rating is going to be from the reviewing phase. A third of the rating will be a public vote, and a third of the rating will be judges that rate the presentations this afternoon. And the results will be presented in the closing ceremony. So without further ado, I would like to present you all the projects that you can see today.
Hi, we are Daniel Holt, Jaume, and Luciano Soares, and we welcome you to 2021 3D UI Contest Fast Forward that presents 3D UI Contest projects.
This year, we have 17 projects selected among 25 submissions. Those projects are exhibited in Expo Hall A, and the authors will be available today at the booths at 2 p.m. Lisbon time to answer any questions and present their projects. The theme of this year was the COVID-19 pandemic.
Projects had to directly or indirectly help to manage and cope with the pandemic situation in indirect or indirect fashions with their 3D user interface projects.
Please do not forget to vote for your favorite projects. The link will be presented at the end of this presentation.
Please enjoy the presentation. The teams look forward to welcoming you in their booth.
Dr. Super is a virtual reality gamified experience aiming to educate medical personnel and the layman regarding the successful execution of the intubation procedure and ventilator troubleshooting actions. Our implementation places the end user into a simulated intensive care unit where he or she is able to learn about these processes and apply that knowledge into practice.
Hello, we are pleased to present you Rebirth 20. We lived after the COVID-19 and keep preventing against it. The application is composed of two parts, prevention and exercise. The prevention allows to learn about the virus and stop its spread. The exercises are intended to help people who have been infected. 3 types of exercise are proposed: physical training, breathing, and relaxation, from exercise designed by the medical sector. Thank you.
The Picnic Protest is a geolocation AR app. We aim to support the civil rights movement in showcase how Black people fight for equality. We applied 3D models and animations to recreate the 3 most dramatic confrontations and designed a timeline to integrate several valuable archived historical videos and images. Besides, this app will also help students study remotely and independently during the COVID-19 pandemic.
This paper presents a web-based virtual tour pipeline to allow organizations developing a virtual tour experience rapidly, which integrates a 3D environment with avatars to provide visitors with a shareable space. Users from an organization with minimal coding experience can develop a low-cost web-based virtual tour using a 360 camera, the software framework, and the documentation directly from the GitHub repository.
Hello, we present an alternative to video conferencing that allows enriching a conversation by the sense of others' proximity. Each user requires two mobile devices. The first one captures binaural audio and head and hand movements. The second, inside a cardboard head-mounted display, renders an avatar and reproduces stereo sound. This is a low-cost and easy-access strategy to extend reality, because physical distancing is not a synonym of social distancing.
Recent events have resulted in the need to provide quality educational lessons remotely. Informed by slide-based presentation programs, Virtual Demonstrator draws analogy to elements such as text fields, shapes, and slides. The backbone of Virtual Demonstrator is its timeline system, which expands a 3D sandbox application into a temporal design space.
We present a remote adversarial virtual reality game that simulates COVID-19 infection spread and protection protocols inside a 3D environment. The game visualizes the results and effects of the transmission on NPCs walking around the supermarket. The two opponent players can be informed about the different directions of the airborne virus transmission and the safety guidelines while trying to achieve their goals respectively. Real-time simulation results are visualized for educational purposes, while in-game challenges provide additional information about the virus.
Virtual reality system for invasive therapy is a system to help doctors plan invasive therapies by risk estimation, navigation, and realization. Which path should you use to implant a probe into the patient's body? How close is this path to the optimal endpoint? Our system helps doctors to retrieve this risk information. Our system has possible applications in COVID-19 invasive ventilation treatment and deep brain stimulation.
In this paper, we present the old real-time multi-peer immersive communication system. Basically, it allows capturing and streaming of local scenario by using a simple audio setup and 360 video camera. Remote immersive users can join the experience by using their head-mounted devices. Other users can join the experience easily as well by using other devices such as a tablet, a laptop, or basically their smartphone.
Hi, my name is Daniel, and it is a pleasure to present you our project,
real-time mixed reality teleconsultation for intensive care units in pandemic situations. We present a remote teleconsultation system with avatar embodiment, where remote experts can join a local, fully reconstructed COVID-19 ICU station via virtual reality. The remote experts have access to the local patient data and can guide local experts via augmented reality and synchronized annotations. This way, personal traffic and potential health and safety risks are reduced in the pandemic situation.
Based on the immunology concepts from vaccine working mechanisms, targeted immunotherapies, and an inspiration from the classic science fiction movie Fantastic Voyage, we set our narratives inside a lymph node of the human body, where a user drives a nanobot to deliver COVID-19 vaccine particles to specific groups of immune cells called antigen-presenting cells, which trigger an immune response against the virus.
This project aims to encourage mindfulness about maintaining interpersonal distance in shared public spaces through a multi-user virtual reality experience that simulates shopping in a grocery store. The virtual environment is populated with non-player characters and up to 20 concurrent live users. A dynamic visual effect that reacts to physical proximity in real time and comparative performance metrics are provided for users to reflect on after the task is completed.
We present a VR system to train healthcare professionals to assemble and speed an emergency pulmonary ventilator for COVID patients developed in Brazil by University of São Paulo. The system is composed by a conventional VR system, and each assembly step is presented by an avatar, assisted by animations, and the user receives completion status and precision feedback through controller vibrations and visual aids.
This phone-based augmented reality application provides instructions on how to use an anesthesia machine as a ventilator. This can be important when a hospital has a shortage of ventilators. The user interacts with the life-size virtual anesthesia machine and is led through the necessary steps.
COVIS is a tool using datasets to compare COVID-19 pandemic trends in New York City. Users can manipulate 3D maps, regard height variance attributes of infection rates, select zip codes to identify detailed information while viewing traffic rates, add new 3D maps to the virtual environment for comparative analysis, as well as compare multiple zip code infection rates for more analysis.
Okay, so I hope you all enjoyed the presentations, and I hope you all take a look at Expo Hall A at 2 o'clock to see the projects, which I think are a good demonstration of how our community can also contribute to the current situation in a positive way, of course.
Okay, so thank you all. Thank you, Frank, for this excellent presentation. And so you will be in Virbela, so you can look for Frank directly just by scrolling the names of the participants, or maybe you will be in the auditorium A to start with, and then maybe in another place just after some discussions. So thank you again.
Okay, and we are offline. Thank you so much. And you live.
Hello, everyone, and welcome to the session on redirected locomotion. I am Evan Suma Rosenberg from the University of Minnesota, and I will be chairing this session. We have a total of 6 papers during this session, all of which will be presented live, back to back. Please, as the papers are being presented, type your questions out in Discord, and those will be selected by student volunteers, and then we will ask them during a joint Q&A session at the end of the session. And with that, I'd like to introduce the author of the first paper. The first paper is Adjusting Relative Translation Gains According to Space Size in Redirected Walking for Mixed Reality Mutual Space Generation, presented by Do-Young Kim.
Go ahead, you can share your screen. Thank you.
Hello everyone, this is Do-Young Kim, and I'm currently attending the PhD program at KAIST UVR Lab. I'm happy to present our work adjusting relative translation gains according to space size in redirected walking for mixed reality mutual space generation. In this study, we propose the concept of relative translation gains, a novel redirected walking method, to create an optimized mutual movable space between the AR host reference space and VR client's remote spaces. Asymmetric remote collaboration based on AR-VR HMD draws attention due to the increasing demand for on-tech meetings with co-presence. And for this, it is necessary to create a mutual space based on the host reference space while understanding the client's heterogeneous remote spaces. Our research came up with how we can modify the VR client's original movable space for merging this to the mutual space more adaptively. For this, we focused on applying translation gain in redirected walking, which has the effect of adjusting lengths without coordinate distortion. By applying previous study results about translation gains in redirected walking, we can increase or decrease the VR client space while the space aspect is fixed as the original one. One step further, we wonder it will be better when we can modify only one axis like this, or to increase or decrease the width and depth by different ratios for a more mutual space adaptive transformation. And this concept is relative translation gains. Relative translation gains refer to a pair of translation gains consisting of 2 different translation gains applied to each axis of the floor. In order to apply relative translation gains, it is necessary to estimate the threshold range, which VR clients cannot notice. We define 2D translation ratio, alpha t, as the ratio between x-axis translation gain and y-axis translation gain. Before we estimate the range of 2D translation ratio, we try to figure out the major factor which might influence this range. Relative translation gains are proposed to match the VR client's remote space to the mutual space more adaptively. So the mutual space to which clients access may be a large conference hall, as IEEE VR auditorium where we are in, or in some cases, clients might be teleported to a smaller meeting room like this. We also find some research that users' length perception in VR differ according to the size of virtual environment. So we set our research question as, how do relative translation gain thresholds differ in relatively larger and smaller reference space? For this, we use 2 different sizes of VR conference rooms as a reference space, where the larger conference room is 4 times bigger than the smaller one. We recruited 20 participants and used the pseudo-2AFC method for estimating the threshold. We designed 5 paths for participants to experience various perceived speed from given relative translation gain conditions, and each participant experienced both larger and smaller room conditions. Results show that the probabilities of larger responses to all relative translation gains in the larger VR conference room were significantly lower than the smaller one, which confirms our hypothesis. This left figure shows the result of feeding the participants' responses to the psychometric function. The threshold range estimated by applying the 25%, 75% criterion is shown in this right figure. And in a larger conference room, when one axis perceived speed is the same as the actual speed, the other axis perceived speed can be 15% slower or 29% faster than the actual speed. In the case of smaller conference room, the other axis perceived speed can be 32% slower or 16% faster than the actual speed. And this indicates that for remote clients connected to the larger reference space, relative translation gains can be increased more to utilize a VR space bigger than their rear space. Reversely, it can be decreased more for a smaller reference space than a larger one. Using relative translation gains as a space modification term, we can generate more wide and optimized mutual movable space for MR remote collaboration compared to the one-to-one square intersection method. And we discussed our result induced by the difference in the horizon's location in a virtual environment according to its space size. When the angle of declination theta decreases, perceived distance in VR is biased to be larger, and which aligns with our results. Based on this insights, we will estimate a more precise threshold range according to the mutual space configuration, such as more diverse size and shape conditions, and existence of mutual objects, etc. In addition, the effect of relative translation gains on VR sickness was not clearly identified in this study, but our future studies will clarify this more closely.
You have now 1 minute.
The contribution of our study is threefold. First, we introduced a novel redirected walking method called relative translation gains that applies different translation gains to the floor's each axis. Second, we show that in order to optimize the effect of relative translation gains, their values should be adjusted according to the size of virtual space deriving from the reference space. Lastly, we suggest how our findings can be applied as a space modification term to generate a mutual space optimized for both the AR host and VR clients in asymmetric MR remote collaboration system. And thank you for your attention, and feel free to ask any questions.
Okay, perfect. Evan?
All right, thank you very much, Du-Young. Now let's go ahead and hear from the second speaker. This second paper is ARC, Alignment-Based Redirection Controller for Redirected Walking in Complex Environments, presented by Niall Williams.
Go ahead, you can share your screen.
Hi, I'm Niall. I'm a PhD student at the University of Maryland, College Park. In VR locomotion, the user explores a virtual environment while located in a different physical environment. It's common for the layouts of these environments to be different. This leads to a fundamental problem where a clear path in the virtual world may correspond to an obstructed path in the physical world. Redirected walking helps to alleviate this problem. It works by slowly rotating the virtual environment around the user while they walk, which causes them to adjust their position. We can use this to steer the user in the physical environment. The speed of the virtual rotations is controlled by parameters called gains. Redirection controllers determine how to apply these gains in order to steer the user. For a given virtual path, there may be many valid physical paths that the user can be steered along. The controller tries to steer the user on paths that minimize the number of collisions. Many controllers have been developed over the years, including steer to center and controllers based on potential fields and reinforcement learning. Different controllers have different assumptions which constrain their decisions. We consider controllers with the following assumptions. There's one user located in a physical and virtual environment. The controller can apply rotation, translation, and curvature gains. And the controller makes steering decisions using only the info available on the current frame. Another common assumption of controllers is that the virtual environment is infinite and empty. This is usually done because we can't test our algorithms in every possible virtual environment. However, this assumption limits a controller's ability to avoid collisions because a large portion of information that's relevant to the locomotion problem is essentially being ignored. To get around this limitation, we leverage alignment. Alignment is a concept of measuring the similarity between two environments with respect to some common feature. For this work, the common feature is the user's proximity to obstacles. Alignment is likely intuitive for many VR researchers, and it's probably something you've done even maybe informally, but to the best of our knowledge, this hasn't really been studied outside of a few recent studies by Thomas et al. Now let's see how alignment can be useful for VR locomotion. Consider this pair of environments. The black shapes are the obstacles and the cursor icon is the user. Because the layouts of the environments are different, if the user tries to walk forward in VR, they'll walk into the obstacle in front of them in the physical world. Now consider this new pair of environments. Notice again that the layouts are different. If the user tries to walk forward in this scenario, they can do so without walking into any physical obstacles. This is because the user's proximity to obstacles in both environments is similar on a local scale with respect to the user's position. So from this example, we can see that even environments can have globally dissimilar configurations, but that there can be regions of local similarity and that these regions lead to fewer collisions. So with this, we were able to develop our algorithm, which is our alignment-based redirection controller, or ARC. ARC compares the layouts of the physical and virtual environments and steers the user towards locally similar positions. It does this by first computing the distance to the closest obstacle to the left, right, and in front of the user. Then, the similarity of the environments is computed as the sum of the pairwise differences of these distances. ARC then aims to steer the user in order to minimize this sum. Full details can be found in the paper. So for example, in this scenario, our algorithm will steer the user towards the middle of the space between the left and right walls in the physical environment, and after some time, their proximity to obstacles in both environments will be the same. Here's a quick demo of user being steered by our algorithm. Here, they get steered away from the track space boundary to their right and towards the center of the track space. And then in the second example, they get steered away from the track boundary to their left and away from the obstacle in front of them while walking in a straight line in VR. And then as they approach the other edge of the track boundary, they again get steered away. We evaluated our algorithm in 3 pairs of environments, and we compared against 2 state-of-the-art controllers, which are steer to center and artificial potential fields. Here we can see a simulated user being steered by ARC, steer to center, and potential fields in an identical physical and virtual environment. The physical environment is shown in green and the virtual is shown in orange. Notice that when steered by ARC, the user's position in the physical world eventually matches their position in the virtual world, and they experience no more collisions. The other controllers, however, continually incur collisions because the user state in the 2 environments is constantly mismatched. Here we can see a heat map of the user's location in the physical space accumulated over multiple paths. Yellow regions indicate more time in that area, and purple regions indicate less time in that area. As the user travels on different paths in the space, they're able to make use of a larger percentage of the physical space when they're steered with our controller, while the other 2 controllers tend to get the user stuck in pockets of space. When we looked at the number of collisions occurred over multiple paths, we found that ARC was able to avoid significantly more collisions than both steer to center and potential fields in every environment we tested. Full details on these results and the numbers can be found in the paper. And then interestingly, we also found that ARC is able to do all of this while steering the user with less intense gains. So normally, a more intense gain corresponds to a greater deviation between the physical and virtual paths, which means that we can steer the user more in the physical world. But this comes at the cost of increasing the chance of simulator sickness because the rotations of the virtual environment around the user in VR becomes more obvious, and it becomes faster and more obvious. So there's a trade-off between the rotation speed, how much we can steer the user, and how comfortable they are. So normally those 2 things are at odds. But here with our algorithm, we were able to achieve better results while also steering the user with less intense gains. So it creates a more comfortable experience too. So in conclusion, We showed that the physical and virtual environments can be globally dissimilar but have locally similar configurations, and that steering the user towards these physical locations that are locally similar to the virtual location can have significant benefits. In particular, our algorithm achieves significantly fewer collisions, it allows the user to explore a larger percentage of the physical environment, and it steers the user with less intense gains, which creates a more comfortable experience. We hope that future work in this area will make use of alignment since it's been shown to be powerful for virtual locomotion. And really quickly, we open source this code. There's a library that we're working on and we'll continuously update it. github.com/pasumi. If you want to work on any of this yourself, it's free and available. Thank you, and I'm happy to take any questions at the end.
Great, thank you, Evan.
Thank you, Niall. Okay, now let's go to the third paper in this session. This is detection thresholds with joint horizontal and vertical gains in redirected jumping, presented by Yi-Jun Lee.
Okay, how about now? How about my slides?
Go ahead.
Okay. Hello, everyone. I'm Yi-Jun Lee from Beihang University. It's a great honor to give the presentation here. Today, my partner Derong Jin and I will introduce our paper, Detection Thresholds with Joint Horizontal and Vertical Gains in Redirected Jumping. Nowadays, free movements in virtual environments are essential for many virtual reality applications. However, traveling in the virtual space is highly constrained by the limited physical tracking space. Therefore, effective locomotion techniques such as teleportation, walking in place, and redirected walking were proposed to offer a better virtual reality experience. Recently, a new locomotion technique called redirected jumping was proposed and investigated. Previous work mainly focused on estimating the imperceptible detection thresholds. For example, the left-related work proposed the concept of redirected jumping and measured the imperceptible detection thresholds. For the right one, researchers measured the threshold of curvature gains. However, they measured detection thresholds individually but ignored the potential effect of combined gains on detection thresholds. In our work, we applied simultaneously horizontal and vertical gains when jumping in virtual environments and estimated the detection thresholds according to user studies. In our design, we focused on two-legged takeoff forward jumping. Firstly, we divided the jumping process into 5 states, which is the same as the previous work, and applied redirection during the ascending and descending states. To detect the jumping state, 3 trackers attached to the user's waist and controllers tracked the corresponding positions. The left video shows the jumping process of the experiment. The participants were asked to jump forward with fixed horizontal and vertical distances in the virtual city environment and experience redirected jumping with varied horizontal and vertical gains. Following a pseudo to alternative first design, after each jump, the participant needs to answer one of 2 questions, shown on the right. We collected user responses to calculate the mean probabilities of longer and higher replies than fitted the 2-dimensional psychometric function. The left graph shows the probability of longer replies to question 1, and the right graph shows the probability of higher replies to question 2. For horizontal gains, the point of subjective equality was defined as a horizontal gain where 50% of the responses to question 1 were longer. Similarly, we defined the lower detection threshold and the upper detection threshold to be the value of horizontal gain when 25% and 75% of the responses were longer, respectively. Vertical detection thresholds are similarly defined based on the probabilities of higher responses to question 2. Viewing from the top, we acquired the 2-dimensional figures shown on the left and the middle to illustrate the probability values within the detection thresholds. We reported the region of interest, a 2-dimensional region bounded by curves of detection thresholds, similar to the imperceptible range estimated by 1-dimensional detection thresholds. gain values inside the region of interest where it's expected to be imperceptible. With increasing vertical gain, a larger horizontal upper detection threshold and a smaller horizontal lower detection threshold could be observed. One possible reason could be that most participants consider the virtual objects on the ground as references. The higher they jumped, the smaller the objects they would perceive, which made them feel the horizontal movement not as obvious. We also observed that as horizontal gain increased, the vertical lower detection threshold became smaller. This was probably due to the fact that once the participants jumped further, they expected to jump higher as well, but the content they saw along the vertical direction did not change as much.
Hello, everyone. I'm Derong Jin, the joint first author of this paper, and I will continue our presentation. Moreover, we developed the two VR games to verify whether the joint horizontal and vertical gains within the estimated threshold could enhance or weaken the user's virtual jumping without catching his or her notice. Both of the two games were based on the two-leg takeoff jump motion. The first game is Box Jumper. The player's goal is to jump on the center of the top surface of the next box. The distance between adjacent boxes is fixed. The second game is Mario Me. The player needs to jump and hit a virtual treasure chest. The distance between the player's head and the nearest face of the chest is also fixed. In these two games, after 8 successful jumps, the player needs to answer questions in order to see whether the player noticed the jumping distance manipulation. We selected 3 groups of horizontal and vertical gains to test our findings. The lower group was within and near the lower detection thresholds. The upper group was within and near the upper detection thresholds. We also used a group that did not manipulate the jumping as a control group. The first table shows the probabilities of longer replies to question 1 and higher replies to question 2. We can observe that the replies were around 50%, which means it was difficult for the participants to tell whether the jumping distances were manipulated. The second table shows the average horizontal jumping distances for the game Box Jumper and the average vertical jumping distances for the game Mario Me. Based on the results of the game applications, a significantly smaller horizontal jumping distance could be observed in upper group compared to that in control group, which confirmed that the redirected jumping technique under the condition in upper group could effectively reduce the required physical tracking space. A similar conclusion could be drawn by comparing the physical jumping distance between control group and lower group, which provides potential insights into rehabilitation exercises. These results reveals the imposed gain indeed affected the participants' physical performance. Regarding jumping actions, in our experiments, we only tested the standard 2-leg takeoff jumps, so the measured detection threshold may not extend to other kinds of jumping actions, such as 1-leg takeoff. Moreover, as for detection threshold, we only explicitly investigated horizontal or vertical ones. We agreed that comprehensive detection thresholds would be a valuable and interesting future work. Lastly, under strict epidemic prevention rules, we only successfully invited a small number of participants with a biased gender. A thorough demonstration study would be our future work. Thanks for watching.
Evan, go ahead.
Okay, thanks to our last speaker. Our next paper is Dynamic Density-Based Redirected Walking Towards Multi-User Virtual Environments, presented by Yue Shen.
Wei-Shen, you can start.
Virtual working allows users to explore larger-scale virtual environments in a limited space imperceptibly. As the figure shows,
5 users are sharing the same limited physical space exploring a virtual library. To realize the requirements of collaborative interaction and reduce economic cost, more and more VR applications are shifting from a single-user immersive experience to a scene that supports multi-use sharing. However, the limited space and growing clinician problems are the challenges that must be solved by multi-user redirected working. Single-user redirection is dedicated to solving physical space constraints. However, when there are multi-user in the physical space, the collision between users will be introduced. The multi-user redirected working algorithms are divided into 2 categories, the reactive algorithms and the predictive algorithm. The reactive algorithm should be improved to decrease the number of collisions. The typical predictive algorithm has the disadvantage of longer computation times and higher dependence on training data sets. In order to solve the above problems, we propose the dynamic density-based multi-user redirected working algorithm. We define a standard density function to determine whether users are gathered. The users in a high-density area are guided to open area. Because of the standard function, a dynamic user distribution with high center density and long boundary density will be formed eventually. The main contribution of this paper include propose a novel dynamic density-based multi-user redirected working method, which can effectively reduce the number of resites. Present a dynamic user density distribution adjustment strategy and a density-based gravity target sighting strategy. Secondly, I would like to introduce the methodology in our paper. The purpose of our method is shown. Then we'll introduce the implementation details by step. The action density refers to the number of users navigating per unit area. DS is designed as a function that is proportional to the number of the user and inversely proportional to the size of the space and the distance from the center. The difference between the actual density and the standard density produces a density force. The double density optimal point gravitational force prevents user gathering to make full use of the physical space. First, we take the ring, where the user with the smallest difference is located as the optimal density ring. Then, our method takes the center of the circle with smallest actual density as the target point. The target point produces gravitational force on all users. Rahman et al. Applied artificial potential fields to redirect. Our experience also used APF to reduce collision between users. The direction of user movement is affected by the resultant force after balance. We generalize density-based reciting method into 2 users and the multi-user. When the user is about collision, the DDBR will be triggered. The turning user turns to open area that is below the standard density. The collision-free state will release when the user reaches the reset target point. Now we move to the part of the experiments. We evaluated the effectiveness of our algorithms using simulation experience. In experiment 1, we test the algorithm performance under the different room size and the number of users. That's an example of user motion track in virtual environments and the physical space. The line chart reflects the average resize, and the histogram shows the average physical distance from the center. Results analysis shows that smaller space and more users both lead to a significant increase in the number of resites. The size of the physical space is the key factor that determines the average physical distance from the center. And the number of the user navigation at the same time is limited by the space size. In experience 2, we designed a point game to compare the DDB RDW algorithm with the dynamic APF RDW. In point game, the occupied point randomly appeared. Users always use the strategy of selecting the occupied point with the largest area. The comparison results are shown here. The results indicate that DDB-RDW has a better performance in reducing resight, and it can reduce the average physical distance from the central area. The performance of occupied area show that DDB-RDW has more advantages in making full use of the space. However, the DDB-RDW may introduce more user cognition as the number of use increase. To be closer to real navigation needs, we designed a library science to test the performance of our algorithm in practical applications. The user starts from the boundary of the library to find the target bookshelf. As a result, in the table show, our algorithm was better in reducing the number of resets. Now we come to the last part, conclusion. We evaluated the performance of DDB-RDW in different science and applications. DDB-RDW effectively lowered the level of the clinician by 30% and shortened the physical distance from the center by 17%. In the future, we will focus on improving the adaptability of DDB-RDW in the physical space with obstacles. That's all for my presentation. If you have any question, please contact me. Thank you.
Thank you so much. We go back to Evan.
Thank you very much. Our next talk is Live OBJ, Object Semantic Based Viewport Prediction for Live Mobile Virtual Reality Streaming, presented by Sheng Wei.
Go ahead. You can start.
Thank you so much for the kind introduction. Hello, everyone. This is Sheng Wei. I'm an assistant professor from Rutgers University, and I'm happy here to present our work on live viewport prediction. And this is jointly done with my students, Xiang Feng and Zeyang Bao. So here we're talking about the 360-degree immersive video captured live and streamed to the user VR headset. During the video playback, the users can freely move their head and watch an arbitrary viewport on the 360-degree sphere. So this gave the user immersive experience, but this setup actually creates a situation where the video that the user actually watched is much smaller than the original video. So this actually creates a challenge, both the challenge and the opportunity in terms of bandwidth consumption. So for the challenge, because if we require a high resolution for the user's viewport, it means that original video would be very huge in size to consume the bandwidth. But it also provides us opportunity that we can actually just stream the user's viewport because that is only part the user will be watching at any single point of time. So this actually motivates this tile-based select streaming approach in the community to reduce the bandwidth consumption. So here the idea is that, okay, so we can actually divide the original frames into multiple tiles, and each tile can be individually encoded into different resolutions. So then if we can encode only the user viewport in high resolution and the other tiles in lower resolution, that can reduce the bandwidth consumption while not impacting the user experience because the user is only watching this high resolution tile. Okay, so the key step here to make this work is actually for the server to predict the user's viewport. So the server needs to know where the user will be watching so that it can encode that part of the video into high resolution. So this is actually the viewport prediction problem that we're trying to address here. All right, so there are existing approaches. One category of approaches looking at this using the historical user and video data, trying to build a heat map model or a deep learning model to predict the user's viewport. But this kind of approach actually requires the access to the historical user video data, which is not available in live streaming scenario. It only works with the video on demand streaming. So looking at live streaming, actually, there are several approaches proposed in the recent years, including two from our own group. So they actually try to capture some signals from the live video to predict the user's viewport in the current live session without requiring historical data. But these individual approaches, they have limitations in terms of accuracy and bandwidth savings due to the limitation of the signal they're trying to capture as a basis for viewport prediction. So in our work, we try to analyze the user's viewport by using this user head movement data set. So here I'm showing an example. If we look at the player C in this immersive video, the player only takes about 5% in terms of the physical space in this frame, but the users would watch this player for more than 40% of the time during the video playback. So this means that users tend to watch meaningful objects and they care more about the semantics of the objects than the spatial properties. So this motivates us to actually use the object semantics as the basis for viewport prediction. And we developed this approach called live OBJ, where we want to predict the user's viewport given a video stream. Our first step is to detect the objects, meaningful objects in this frame, and try to track these objects for the user's viewport. But the problem here is that there could be multiple meaningful objects in this frame. So we don't really know which one the user will be following. So that's why we actually leverage the user feedback. We use the user traces from the current live video session, but for the segment that user has already watched. So use this as a guideline to basically narrow it down to just one or a small number of objects to track. So this could work, but due to the dynamic VR scenes, the detection tracking chain might break due to the limitation of the algorithm. So we further introduce a reinforcement learning-based modeling mechanism to combine the video stream and user trace, and we build a Q-learning-based approach where we create a Q table for each tile in the frame, and we at the online stage we try to determine the best action to take in terms of whether either including or not including this tile into the viewport to improve the prediction accuracy. All right, so we implement this approach, and we did evaluations using a public user data set and using the metrics of accuracy, bandwidth consumption, and processing delay. And we compare our approach with 5 baseline methods. So we observed that our live OBJ approach achieves high accuracy with a low error duration, meaning even if there's a prediction error, it can recover from the error in a timely manner. This is very important for user experience. And also we observed that our approach achieves a low bandwidth consumption, about 50% of the original bandwidth. And we can get low processing overhead. In most of the frames, we can get below 200 milliseconds for each frame. So this means if we use a subsampling approach, we can, for example, process a small number of frames in every second, we can achieve the real-time performance for live streaming. So in conclusion, we target the viewport prediction problem in live VR streaming, and our solution is the object semantics-based method. And we achieve high prediction accuracy and low bandwidth consumption. And more important, our approach actually meets the real-time live streaming requirements. So last but not least, I would like to thank our sponsor, and also we open source our project on GitHub. We welcome the feedback from the community.
Okay,
thank you so much.
Thank you. Evan, go back to you.
Thank you very much. And now we have one more paper left to present in this session before moving on to the Q&A. The paper is Walking Outside the Box, Estimation of Detection Thresholds for Non-Forward Steps, and the presenter is Young-Hun Cho.
Go ahead, you can start.
Okay. Hello, everyone. I'm Young-Hun Cho from Yonsei University, and we are happy to present our paper, Walking Outside the Box, Estimation of Detection Threshold for Non-Forward Steps. So redirected walking manipulates the user's viewpoint, creating a discrepancy between the physical orientation and the virtual viewpoint. By doing so, the user can explore a large virtual environment in a small physical tract space. So applying redirected walking or applying gains lead to efficient space usage and immersive experience. And gain is applied until the detection threshold, which is a boundary that the user does not notice the gain. But however, the most redirected walking algorithms focus on the forward steps. However, to unlock the freedom on locomotion in VR, we think the non-forward step should be included as a possible option. Such non-forward steps can be used in various situations. Sideward steps can be used when walking through a narrow path, such as wailing, or backward steps can be used while running away from the enemy or adjusting missled steps. In this work, we will measure detection threshold for non-forward steps. So we designed an experiment to measure detection threshold for non-forward steps. We tested it 6 cases where translation gain and curvature gain are measured for backward, left sideward, and right sideward step. We included the left and right sideward step separately because they might show different results. And there are 2 possible scenarios in the sideward step. The user's viewpoint can be parallel or perpendicular to the user's walking direction. When curvature gain is applied, the user unknowingly compensates for the rotated viewpoint. However, if the user's viewpoint is perpendicular to the walking direction, the user cannot compensate because they are not watching the walking direction. Therefore, we instructed the user to walk so that the viewpoint is parallel to the walking direction. For the detection threshold experiment, we needed to set up a gain range for translation and curvature gain. We started from Steinig's original work's gain range. In a pre-test session, we found that the translation gain range is usable for non-forward steps. However, the curvature gain range was too narrow for the non-forward steps. So we extended the curvature gain range using different curvature gain ranges for backward and sideward steps. We used a conventional pseudo-2AFC method to estimate the detection threshold. The user walks through 4 meters with the gain applied, and they're asked to choose between the 2 answers. In the curvature gain experiment, the users are asked if their path was curved right or left, and in translation gain, the users are asked if their virtual movement was greater or smaller than the actual movement. The results are fit to the sigmoid function to estimate the PSE and the detection thresholds. We recruited 18 participants for the experiment. The left figure shows the backward curvature gain, and the right figure shows the sideways curvature gain. These figures show the result of the backward translation gain, left side step translation gain, and right side step translation gain experiment. The overall detection threshold for non-forward step are similar to that of forward steps. However, backward step detection thresholds were bigger than the sideward step, especially on the upscaling threshold. And these figures show the result of the backward curvature gain, left side step curvature gain, and right side step curvature gain. Compared to forward step detection threshold, both backward and sideward step detection threshold were bigger. The backward step had a curvature radius of approximately 10 meters, and sideward step had a curvature radius of approximately 5 meters. Note that the detection threshold of sideward step are tilted to the side in both experiments. The detection threshold for the backward step are bigger than the sideward step, especially on the upscaling threshold. We believe this is because the relative distance between the user and the target. In a backward step experiment, because the user gets farther from the target, they become less sensitive to the movement. On the other hand, in the sideward step experiment, they become more sensitive to the movement because the user gets closer to the target. This figure shows the range of detection threshold in sideward step. It is a quite interesting result. The threshold is bigger on the front side of the user's body than the back side of the body. We believe this is because of the dynamic structure of the sideward step. When walking sideways, the user's head is rotated to the side, viewing the same direction as the walking direction. However, because turning the head 90 degrees is very awkward, the user's head is slightly pointing towards the front side of the body. Therefore, when moving sideways, the user tends to favor a slight front movement rather than the backward movement. Thus, compensating a big forward movement is relatively comfortable and natural than the backward movement, thereby having bigger threshold on the front side of the body. And Ness et al. Has shown that having lower velocity leads to higher detection threshold for curvature gain. Therefore, we have measured the average velocity of participants to show the effect of the velocity. The results showed that sideward step was significantly slower than the backward step, which can be one of the factors that the sideward step threshold are bigger on the curvature gain.
Yes.
In this work, we have proposed detection threshold for non-forward step. The results show that non-forward step have similar translation gain and bigger curvature gain detection threshold compared to forward step. Non-forward step can be used in general redirected walking algorithm, enabling movement towards any directions. If VR application mainly uses non-forward steps, higher redirection is possible with bigger detection threshold. Thank you for listening.
Okay, perfect. Thank you so much. We now move on to the Q&A.
Okay.
When you're ready, let me know.
I'm ready.
Okay, so let's go. 3, 2, 1, and go live.
Okay. First, I'd like to awkwardly clap at my camera to thank all of our speakers. All right, so we are now going to move to the live Q&A. Some of the authors have already answered some questions in the Discord. However, I'm going to select some questions that may have already been partially addressed, mainly because otherwise we'll have no questions to ask, and also for the benefit of the people who are watching the Twitch stream. The first question was directed towards the first paper about relative translation gains, but it actually is a really important question, and it applies to all three of the detection threshold studies conducted in 3 different papers in this session. So I'm going to ask the question as asked, but this is actually, we should consider broadening the scope of this question and hearing from all 3 of those authors. Tabitha Peck asks, differences in thresholds have been identified between men and women for threshold detections. Your study was performed with only 6 women out of 20 participants. How do you propose your results be adapted to account for the lack of the diversity in your sample population? And I would also again note that all 3 of the authors that presented studies like this could potentially chime in on this question.
Yes, thank you for your question. And in this study, we focused on seeing the difference of the threshold range according to the size of the virtual environment. And since all participants experienced both size condition as a between subjects, so we thought it would be okay to compare the threshold according to the size. But as you mentioned, there will be a significant differences in the threshold range because men and women have a different average height or IPD, etc. So to apply this redirected walking method, we need to consider some individual differences according to users. And we're also working on how can we measure a more customized threshold for each user. So that which not only consider genders, but also some physical or psychological differences according to participants. So we're now just considering some vital signal data, something like EEG by decoding the EEG data or sort of that things. But yes, definitely, as you mentioned, we need to consider the gender issue for estimating the threshold.
Thank you. Do any of the other authors have any comments about diversity in the samples? Okay, then I will move on to selecting another question. So this, I'm actually going to combine questions here. This is aimed towards Niall Williams. One question from Felix Thiel said, very cool, maybe I missed it, but how does your algorithm know how the real environment looks like? Does it need to be fed in before? And a follow-up question by Love Coley asked, could you use something like a HoloLens or Magic Leap to dynamically build up the geometry of the environment and adjust accordingly? Or does the geometry need to be pre-processed in some way?
Yeah, so for this work, like in the demo we showed in the presentation, we worked with an Oculus Quest, which, for example, does not have access to the camera data. So in that case, we had to give it the layout of the physical space, but we don't have to give it the layout of the virtual space. And the way we compute the distances is just with ray shooting queries. So you take the user's position and then you shoot a ray until it hits an object, which is normal for graphics people, I guess. So doing that in like Unity is really easy and works in whatever environment because you have all the data there. But yes, for the physical world, it's a bit more of a problem. Depends on your headset and what data they let you access. And the short answer to Love's question is yes. Yeah, you would want to, you can do something dynamic. It doesn't have to be pre-processed. If you can get it in real time, that's fine because it all works in real time.
Great. I'm going to move ahead and jump to another paper just so we can get some target different authors. This question is aimed towards Yi-Jun Lee. And this comes from Rob Lindemann. It says, nice exploration of redirected jumping. For Mario Me, did the subjects look up to hit the chest or were they looking down? Do you think view direction makes a difference due to different visual cues?
Thanks for your question.
Yeah, you go first.
Thanks for your questions. From our intuition and also our pilot study, we do think that view direction will make a difference due to different visual cues. So in the experiment for the game Real Me, we required subjects looking forward when they perform the jumping actions. And also we required nothing when before they jumped. And from the results of our experiments, most of the subjects would look up to the chest before they perform jumps, and also they look forward when they perform the jumping.
Okay. Next question. This one is going to be aimed towards Sheng Wei and co-authors. Comes from Pablo Figueroa. Great work. Thanks for using an open source license. I wonder if you define a limit on the speed in which a user should turn his head so he doesn't see the limits where you are changing the resolution of the streaming.
Yeah, that's a very good point. So I think that in immersive video streaming, we tend to not limit the user's behavior. We don't want to set a limit telling the user, okay, how fast or slow you should move. But I think this is a very good point that we could actually try to observe the user behavior, like the speed of the movement, and then adapt this resolution of the video, right, to maximize the perceivable QoE, because that would depend on the user movement. I agree with the point here in this question. So I think that can be leveraged to find an optimal resolution for the video.
Okay. Next question. This one is aimed towards walking outside the box from Doug Bowman. In the experiment, I think you said that during sideways steps, participants turned their head in the direction of movement. But in real VR applications, using sideways steps, example VR gaming, users might be facing forwards while stepping sideways. Would this change your results?
Yeah, thank you for the question. That is actually a great question. We have actually tested both cases where the user is facing front or facing sideways. And if the curvature gain is applied, the user have to compensate for the secretly rotated viewpoint. But if if in the virtual environment there are no reference points or a very empty VR space, if the user is facing front, the sideward step curvature gain might not work. So if there's a close reference point or an object in front of the user, that could work.
Okay, I'm going to move back to a question for Niall Williams. This question, I believe you addressed in Discord, but I'm going to tack on an addendum as well with my own question that I was wondering about. So the original question was from Ayush Bhargava: what happens when a user tries to deliberately walk towards the obstacle? And the addendum I'll add is that in Thomas et al., one of the motivations for introducing alignment was actually to explore integrate passive haptics with redirected walking. And so I'm curious if you are thinking about or are planning to do any work that tries to apply ARC in the context of physical interaction.
Yeah, so for the work we presented, it does assume that the user will not walk into any obstacles in the virtual world. If the user is walking into obstacles in the virtual world, if they're supposed to do that, if it's like an object they're supposed to walk into, I think you would just ignore it. Like in your race shooting queries, you just wouldn't consider that object. If it's not an object they're supposed to walk into, I'm not sure what would happen. Our algorithm as it was presented would definitely not work as it's intended. You'd probably have to come up with some sort of edge case to handle that. Probably just turn off the redirection. I think that's probably the best, but I think you might have bigger problems if users are walking into obstacles in VR deliberately when they're not supposed to be. And then Evan, for your extra question, yeah. So this work, our work, passive haptics is not the motivation. Our motivation was to avoid obstacles, but in the physical world. But yes, that is definitely one of the things that this alignment concept enables, and you can sort of do with the work by Thomas et al. Or us. But one of the issues there, we haven't like conducted any studies or anything. Just thinking about it is the actual angle that the user approaches the object at in the physical world will matter, because if, for example, they approach a wall in the virtual world that's at a certain angle relative to them, and then they try and touch it in the virtual world, if they can be close to the wall in the physical world, but maybe at a different angle, and that's going to affect how they feel the physical wall versus the relative wall or the virtual wall. So it can be used, this sort of a concept can be used for passive haptics in like a general sense, which is quite an interesting thing, because usually passive haptics and redirected walking don't go together. But we haven't done any studies on it, and I think you'd have to do a lot of studies to see how people handle it, because another thing is that it doesn't guarantee passive haptics. It would be like very partial. So that might be more jarring to the user than having no passive haptics at all.
Yeah, it's definitely an interesting area, wide open for future work, and it kind of also overlaps a little bit with Love Coley's work on redirected touching. We have time for one final question, so I will select one that was added while we were talking from Keigo Matsumoto. This is aimed towards the authors of Walking Outside the Box. Is it conceivable that the game could also change when walking while bent over?
Sorry, but I'm not sure what walking while bent over means. Is it mean the torso is bent, or?
I think if I'm interpreting Keigo's question correctly, that yeah, he's asking about whether, you know, if you're bending over with your torso and not looking up straight.
When not looking up straight, I think it might change the threshold of the detection threshold for the non-forward step and for the just forward steps, because I think one of the points in my work is that non-forward step is not a very mainly used or very natural movement while walking. So there is a slight different feeling when you're walking sideways or backward rather than walking forward. So if you bent over, I think the gain threshold will change, definitely.
Okay. All right, I'm being told that we're at time. So once again, let's thank all of the speakers in this session. Very nice talks. For the questions that we did not get to during the live Q&A, please go ahead on Discord and feel free to answer those questions directly in that platform. With that, I would like to thank everyone for attending, and I will conclude this session.
Thank you.
Everyone.
Thank you.
Goodbye.
free interaction. My name is Doug Bowman from Virginia Tech in the United States. And in this session, we have 5 papers, all of which are going to be presented live by the authors. As in other sessions, we'll have 7-minute presentations, and we'll do all of those back to back, followed by a joint Q&A session. So as you have questions while you're listening to the presentations, please put them in the Discord under the appropriate channel for each paper. So with that, let's go straight to the first paper. It's entitled Blink Suppressed Hand Redirection, and this is going to be presented by Andre Zinner.
Well, thank you very much, Doug, and hello, everyone. My name is Andre Zinner, and I'm a doctoral researcher at Saarland University and the German Research Center for Artificial Intelligence in Saarbrücken, Germany. And in the following, I have the honor to present to you the work of my co-authors, Cora Regitz, Antonio Krüger, and myself on the subject of blink-suppressed hand redirection. In our paper, we investigate a novel approach to implementing unnoticeable hand redirection, also known as body warping, which has been shown in previous research to enhance proxy-based haptic feedback and the ergonomics of 3D user interactions. Traditional hand warping techniques, such as sketched here in this animation, gradually offset the virtual hand rendering from the real hand position in order to invoke a compensation movement. And this compensation then affects the real hand trajectory and leads the user's real hand to a dislocated physical target, while the virtual hand ends up reaching a virtual target. So far, however, hand redirection research has not yet investigated techniques that make use of change blindness as induced, for example, by visual suppression, such as, for example, during eye blinks. However, these short moments of temporary blindness have been successfully used in past research to improve, for example, redirected walking by covertly manipulating the virtual environment, as we have also seen today already in the keynote talk. And so to start filling this gap in research, in this paper, we propose a first algorithm for blink-suppressed hand redirection, short BSHR. And our algorithm is based on the hand redirection technique by Cheng and colleagues, which was published in 2017. Our variation of this algorithm basically is designed to allow for an investigation of the concept's general feasibility and its detectability. Our investigated technique supports 2 modes of operation, and the first one is called instantaneous BSHR and does not add any hand offsets while the user's eyes are opened. When closing the eyes, however, during a blink, as shown here in this animation, the complete offset between a real target and a virtual target is instantaneously added to the hand rendering. As the user then closes in again towards the targets with opened eyes, this offset remains constant and no additional warping is applied. The following video demonstrates our implementation of this first version of the technique, with the green hand rendering here highlighting the real hand location for illustration. The second mode of our algorithm then combines this idea of instantaneously injecting hand offsets during a blink and a traditional approach of continuous hand warping. And in order to achieve unnoticeable redirection here, the virtual hand is gradually offset from the real hand location when the user's eyes are opened, but the redirection is restricted to an amplitude below detection thresholds. During a blink then, our technique instantaneously changes the hand offset in a way that, when compensated for, enables the user to reach the targets again with continued unnoticeable warping. And in order to implement this, the second mode of our algorithm is parameterized. So specifically, the algorithm takes as an input information about how much hand redirection can go unnoticed by users. And this input is provided in form of the detection thresholds that we assessed in our IEEE VR 2019 paper, consisting of the maximum hand redirection angle, as well as the minimum and the maximum gain factors that can be applied without users noticing it. These parameters are then used within our algorithm to estimate an area of unnoticeable redirection, indicated here in red. And by raycasting against this area from the virtual towards the real target, our algorithm then determines a dummy target location, which is used as the physical destination point for our unnoticeable warping. And all the remaining offset that cannot be covered by unnoticeable hand redirection, so the distance between the dummy target and the real target, will then be applied during a blink. The following video also showcases the second mode of the algorithm. For more details, please refer to the description that we provide in the paper. Now, in order to investigate how much hand redirection can go unnoticed with this approach, we conducted a psychophysical user experiment, and by applying an adaptive interleaved staircase method, we derived the detection thresholds of 4 different conditions along these 3 different representative directions. And in the first condition here, we evaluated the first mode, instantaneous blink suppressed hand redirection, which does not involve any continuous warping. 2 further conditions then evaluated this second mixed mode of our algorithm, once using very conservative parameters, just using 50% of the detection thresholds for the gradual warping, and once using 100%. And finally, in a baseline condition, we assessed the conventional algorithm by Chang that does not leverage blink suppression and just applies unlimited continuous warping. And so in our experimental setup, we tracked the participants' calibrated fingertip location, as you can see here in this video, and participants then repeatedly reached for a virtual target in VR while different amounts of hand redirection were applied following the staircase method. And once they touched the virtual target in VR, they then just answered a simple yes/no question, asking them whether they perceived any manipulation of the hand, warping or hand shifts during the interaction. Summarizing the results, we could prove the practical feasibility of this instantaneous blink suppressed hand redirection as in mode number 1, and found the detection thresholds of this technique to be significantly greater than 0 centimeters and generally of the same order of magnitude as the thresholds that were found previously for other conventional approaches. The results for the rightwards and downwards direction further indicate that when combining instantaneous hand shifts during blinks and continuous warping below the detection thresholds, then the range of unnoticeable hand redirection can be increased compared to what can go unnoticed just using instantaneously injected offsets during a blink. And very finally, our analysis now also revealed the previously unknown detection thresholds of the popular baseline hand redirection technique that was published by Chang and colleagues. So to conclude, while our results here show blink suppressed hand redirection to be a promising technique that in our view merits further exploration, we also like to note that the algorithm as proposed in this paper still works only under certain assumptions. For example, it requires the user to blink during the reach and before the hand enters the visual focus area. In order to then derive a universally applicable technique in future work, we like to showcase and study how mechanisms could be integrated that ensure a correct redirection, even if the user does not blink validly during the reach interaction, or that unobtrusively trigger blinks on demand. And very finally, we also aim to leverage saccadic suppression in future iterations of our technique. And this concludes my talk. So thank you very much for listening, and I'm very happy to take any questions later in the Q&A session. Thanks.
Yes, which is me, I guess.
Yep. So are you ready?
Yep. Let me share my screen quick.
So thank you very much, Andre. Again, if you have questions for Andre and any of the authors, please put them in Discord and we'll ask them at the end. The second presentation in the session is entitled Flash Pen, a high fidelity and high precision multi-surface pen for virtual reality. And it's going to be presented by Hugo Ramat. Hugo.
So hello everyone. So today I'm going to present Flash Pen, a high fidelity and high precision multi-surface pen for virtual reality that I did at the Sensing Interaction and Perception Lab at ETH Zurich. So pen interaction is becoming a commodity input modality on interactive devices such as the iPad or Microsoft Studio. It has been shown to help externalize thoughts via annotation and note-taking, as well as to enhance visual thinking. And people perform active reading by jotting down annotation, writing comments, or while reading a document. However, such medium can be used in a lot more contexts, such as precision to paint, to draw, to fill shapes, or even to interact with the user interface, such as sliders and buttons. And with the growing availability of VR applications and platforms, designers and researchers have started to explore the capability of supporting pen input for sketching. To do so, current VR sketching applications track the user's hands or controllers through cameras built into the headset or externally, mostly to sketch in midair with like a tilt brush or gravity sketch. Such systems are limited by the tracking system resolution and frame rate of the camera used for registering the input. Other systems have investigated the use of a tablet to gain in accuracy. However, even if we gain in precision and accuracy, such tablets need to be carried by the user or laid down on the flat surface, and the input is limited to the tablet surface. So in this paper, we present Flash Pen. Flash Pen is a VR pen input device that brings pen input quality to VR systems. So we demonstrate Flash Pen precision and mobility in several apps. So first, a painting app, which allows users to accurately fill shapes and interact with widgets such as sliders. In another example, a user is exploring a multi-layer map with a magic lens. The map has two layers. The first layer is a geologic map, and the second one is a satellite view, seen through a magic lens. The user can use the pen as a precise manipulation tool to drag the magic lens around, revealing the satellite layer. In the next app, an annotation application, a user can browse their document library to select a specific article to review. The user can highlight important parts, jot down comments, and emphasize paragraphs of interest. And in the last application, we use the high sampling rate of Flash Pen to design motion experiences where the user draws strokes using varying input speeds to create a path animation of a plane. So our prototype reappropriates an optical flow sensor found in gaming mice. It can be used on a flat surface at different orientation with a wide range of supported surface materials. So Flash Pen captures optical reflection at 8,000 frames per second. It registers movement of 1/226th of a millimeter. Relative motion is inferred from the optical sensor, digitizing pen stroke at a rate that is approximately 40 times higher than the other stylus, such as Wacom or Microsoft Surface. So we use the OptiTrack for determining the absolute position of the pen. And Flash Pen is tracked by the camera at all times, because when users write, they must slightly arc their writing, thereby gradually changing the rotation of the pen and thus the perceived direction of writing. And such rotational movement bias the track location if not accounted for. So to evaluate those opportunities with our prototype, we conducted a user study using a within subject design in two different contexts, a tracing block and a writing block. The aim of the tracing block was to gather quantitative data about Flash Pen accuracy of the pen input by measuring the user performance in tracing task. We deliberately focused on low-level aspect of interaction, avoiding higher-level cognitive process, so just tracing and reproducing a line. So to this end, we choose two devices, Wacom Pen and Flash Pen, two instructions, as fast as possible, as accurate as possible, 4 shapes, wave, rectangle, circle, and triangle, and 3 sizes. And in the writing block, we investigate the impact that each device had on writing. For this, we compare the device with each other while writing sentences. So we compare 8 sentences with 3 devices, the Wacom, the Flash Pen, and the analog pen. To better understand the results, we're going to look at the accuracy, which is the shortest distance between each point of the stroke drawn by the participant and the reference pattern. So participants reporting having no trouble interacting with one or the other device, and they stated that they were accurately reproducing the pattern in both conditions. So participants found it hard to follow the small shapes as the pattern to follow was tiny and led to more errors. However, Those were drawn more accurately than medium and large shapes because they stay in the range motor of the end. And we finally found that circle and square had similar accuracy, while the same was true for triangle and wave. A simple explanation is that drawing wave and triangle patterns are performed with a series of more natural end motions, while the other shapes require interleaving horizontal segments, breaking the flow of handwriting. So overall, FlashPen and Wacom have a similar accuracy when following trace on the screen. So this illustration, they speak the same sentences written by the three devices in our study. We can see that the fidelity of FlashPen and Wacom match the fidelity of the analog pen in terms of shape when disregarding scale. And during fast movement, for example, at the end of a letter stroke, points produced by the Wacom pen are much more spaced than using FlashPen. Also, because current pens do not deliver dense enough samples of the pen position to compose a curve, digital pen systems need to interpolate between raw points to infer the small micro movements of the pen. And those interpolations and prediction technique can lead to errors and a lack of precision. And due to the higher sampling rate of FlashPen, the interpolations are much shorter and thus causes the overall input to exhibit higher fidelity. So FlashPen is a novel input device that allows users to precisely sketch and draw at a high sampling rate, enabling the almost perfect reconstruction of the analog pen motions. So for the future, we envision that our research prototype can be reconfigured and be made more ergonomic and more portable. So thanks for your attention, and I would be happy to answer the question at the end.
All right, thank you very much, Hugo, for that interesting talk. Our next paper is Design and Evaluation of a Freehand VR-based authoring environment for automated vehicle testing. And this is going to be presented by Sevinç Eroglu.
Is it? Okay, yeah, hi, my name is Sevinç Eroglu and welcome to this talk on design and evaluation of a freehand VR-based authoring environment for automated vehicle testing. So VR is increasing the use for safe testing of automated vehicles. And to create these testing environments, engineers typically use desktop-based authoring tools. However, this requires expert knowledge. Furthermore, to perform design modifications during the testing, the user has to leave the virtual environment. And this breaks the immersion and, more importantly, slows down the design and evaluation cycle. So scene authoring inside VR enables faster design iterations. And to this end, we propose an authoring environment to design road networks and traffic scenarios based on freehand interaction. And to achieve a fast and efficient workflow, we devised a novel interaction technique for object placement and selection on a 2D panel. So in this talk, I will focus on our proposed interaction technique. And please check the paper for more details about the authoring system. So designing a road network structure is a primarily 2D interaction task. Therefore, we design a scene control panel that consists of a 2D wall in miniature. In our technique, the pointing ray is divided into colored sections that represents the different actions. So object placement and selection are triggered based on the distance of the index finger to the panel. Here you can see how objects are added into the scene, and the creation can be observed immediately in the environment. So all objects can be selected afterwards to be modified or removed from the scene. To evaluate our indirect technique, we perform a within subjects user study with 16 participants. Our goal is to provide a tool for road network authoring that is fast and offers a precise placement of objects. Therefore, we compare our indirect technique to a direct interaction technique regarding task completion time, precision, and usability. So the direct interaction is inspired by the work of Cott et al., where users create roads by placing control points directly on the terrain. And the navigation is performed by using two-handed gestural inputs. So we investigate the following hypothesis. Regarding task completion time, precision, and preference on road creation, we expect that indirect will outperform direct interactions. And based on previous works, we expect that direct interaction will be preferred for object placement. So regarding task completion time, the task is to add a sequence of control points onto predefined target locations while being as fast as possible. And to achieve this, both selection and navigation have to be performed. And regarding the precision tasks, participants were instructed to be as precise as possible for adding the control points without time restriction. So in the direct condition, navigation is performed by using two-handed gestural input, and it is enabled when the user performs the grab gesture with both hands. Moving the grab hands apart or closer, zoom in or out is executed respectively. Objects are added onto the terrain via the indicator that is attached to the index fingertip. Participants were instructed to be as fast as possible in the task completion time and as precise as possible in the precision task. So based on the results, we found a significant difference in the task completion time, and indirect outperformed direct in terms of speed. Thus, we can accept our hypothesis 1. For task completion, we recorded the time that they spent on the selection and navigation individually. And we observed that there is no significant difference between the selection techniques, while the trouble technique in the indirect condition significantly outperforms the technique in the direct condition. This result indicates that the overall task completion time is affected by the navigation rather than the selection technique. And concerning our hypothesis 2, we found a significant difference in terms of precision. So we can accept our hypothesis. Regarding hypothesis 3 and 4, a 7-point Likert scale subjective questionnaire was designed to be ranked after each of the conditions. Based on the results, indirect significantly outperformed direct regarding road creation and object placement. This confirms our hypothesis 3, but not 4. One possible reason is indicated by the qualitative feedback that we obtained during the study. So some participants found traveling by zooming with both hands to be less ergonomic than traveling via the 2D panel. To conclude, we presented our system to create road networks and traffic scenarios based on freehand gestures. Furthermore, we devised a novel interaction technique to add and select objects on a 2D panel. And to evaluate the performance of our interaction technique, we conducted a user study in which we compare our approach to an existing freehand interaction technique. The results show that our indirect technique outperforms the direct interaction in terms of speed and precision, as well as usability and intuitiveness. Well, we believe that our technique performed particularly well for this task since it addresses the 2D nature of the road network design problem. That brings me to the end. Thank you for listening, and I will be glad to answer your questions.
All right, thank you very much, Sevinch. Appreciate that interesting presentation. We will move on to the 4th paper, and this paper is called Hands-Free Interaction in Immersive Virtual Reality, a Systematic Review. It's going to be presented by Pedro Montero.
So, hello everyone who's watching. My name is Pedro Monteiro, and I'm here to present you a systematic review that me and the team did on hands-free interaction in immersive virtual reality. So why this systematic review? As you know, nowadays, the main interface for interaction in VR are the controllers that are available with most VR systems. They enable point-and-click interaction metaphors in VR, and as such, much research is already available regarding that topic. There is a lot of research on 3D user interfaces, on how to integrate 2D menus in VR, and even natural navigation. But picture a future where VR is so immersive that we do not need these controllers. And not only the future, but today, when hands are already being used to perform natural manipulation on virtual objects. There are situations where interacting with a VR system is not feasible with hands and by extent with controllers. That is the gap we found. Put simply, what if we do not have hands to interact in VR because they are already being used? And so we set systematize and provide an overview of current literature and opportunities in this area. Our goals are to identify which hands-free interfaces are currently used to interact in the virtual environments, identify which interaction tasks are performed using these interfaces, identify which metrics are used to evaluate the interfaces, and understand how the interfaces perform in the context of those metrics. To meet our goals, we did a systematic review of the literature using the PRISM methodology. We defined a set of inclusion and exclusion criteria for the studies and performed the search in 3 major electronic science databases on May 14, 2020. We analyzed 1,349 records, and through the criteria, we filtered those records to 80 valid studies. You can read more about the methodology on the manuscript. So what did we find? We have enumerated every interface we found and categorized interfaces following a taxonomy that contemplates the source of interaction, modality, and hardware. This taxonomy is one of the main contributions of our work. Here you can see the interfaces that we have found. There are 3 main interface sources that account for about 85% of all sources, which are the voice, the eyes, and the head. 2 of these coincide with the capabilities of the hardware that's already present in today's most used VR setups, the microphones for voice input and the HMD for head tracking. We suspect voice is the most studied interface since it presents the greatest potential between availability, since HMDs already have microphones, and the advent of investment in AI for processing and giving meaning to the voice input. Eye and head tracking seem to be a good replacement for the controllers regarding point-and-click interfaces. Additionally, we also found some more novel approaches, for instance, the use of brain-computer interfaces, the detection of face expressions and foot movements to enable actions in the virtual environments. Regarding the second goal, here you can see the number of studies that use a specific interaction source to accomplish a certain task. These are tasks we have found. By far, system control and selection tasks are the most performed ones in a VR scenario using these hands-free interfaces. We found that voice was the most versatile interface and is used in most of the tasks, for instance, to perform discrete actions on the applications like zooming, changing game state, navigating menus, selecting, creating, and manipulating objects, and perform text input. You can also see that we have divided selection by its 2 phases, point at the target and confirm that selection. And so there is no surprise in head and eye tracking being used to point at objects, as this is a natural behavior. Symbolic input, when not directly performed by speech, is then using the selection interfaces, or as we have found, by using brain signals to perform that selection of keys in a virtual keyboard. In terms of evaluation, 47 of the studies conducted an evaluation of these interfaces, with a high number of studies not performing an evaluation, which we believe is a big gap in the literature. Here you can see the evaluation metrics we have found in the studies. Most of them evaluate usability of the interfaces, and for this, satisfaction is mostly measured with custom questionnaires made by the authors, while few use validated questionnaires. Efficiency is mostly measured using the time it takes to perform a task using the interface or by its performance throughput. Finally, efficacy is mostly measured by recording the number of errors participants made during the trials. Some studies measure the mental state of participants by subjective instruments like questionnaires for agency, sense of presence, and emotional response. Some of these questionnaires are validated, while others are not. Some studies also measure the physical state of participants, namely by surveying how users felt simulator sickness, or for instance, the eye fatigue by how much users' eyes moved. Finally, some studies measure the raw system performance, for example, how fast the system recognizes the user action or word. If we look at the results of those evaluations, we can see a lack of comparison of interfaces. Only 30 studies compared interfaces, and from those, only 8 compared 2 or more hands-free interfaces, with the others comparing hands-free interface with a non-hands-free interface. 25 as statistically significant results. Generally, between eye and head gaze for selection, some studies point to head gaze to have better efficiency, while others point to the opposite. These also happen with satisfaction metrics. These mixed results, which also happen in other comparisons, suggest that interface evaluation is highly dependent on study design and that researchers should pay special care to this before evaluating the interfaces. In studies that compared hands-free interfaces to a non-hands-free interface, which were mostly controllers, the controllers were consistently better, except for system control tasks, where the voice was better in physical and mental states. From the studies, we have found a lot of opportunities for research and improvement of hands-free interfaces. To name a few, a better integration of the interfaces with VR setups, as some are cumbersome to use. and provide meaningful GUIs and interaction patterns for those interfaces. Most importantly, in our opinion, there's a great opportunity for the creation of a test framework that would allow scientific validation and evaluation of these interfaces, resulting in more strong studies. These strong studies would in the end enable better comparisons between current and new interfaces. To end, and as this presentation could not possibly contain all the information, I would like to point you to the paper manuscript where you can read much more and in-depth information of this survey. I'll also be around in the Discord channel this week, so you can tag me anytime if you have questions. Thank you for your time.
Great, thank you, Pedro. So we have one more paper in this session, and this paper is Comparative Evaluation of Digital Writing and Art in Real Immersive Virtual Environments. And it's going to be presented by Roshan Venkatakrishnan from Clemson University.
Well, actually, it's being presented by Rohit, but we're twins, so I'll take that. Thanks for tuning into this talk thanks for getting into this talk that gets into comparing digital writing and art across real and immersive virtual environments. And this is our team, and let's get right into it. So what got us motivated to perform this line of work? We see that VR is increasingly being applied to the contexts of education, training, and medicine, where learning is important. And research has shown that note-taking is an important part of learning. So we wanted to study and find out where contemporary VR systems stand in affording writing and artwork. So let's look at some of the related work that's been done in this area. Pauperev and his colleagues presented an intuitive tablet stylus interaction metaphor for writing in VR, and they found that latency in visualizing the digital output on the canvas presented an issue for users that are performing the drawing or writing tasks. And traditional sketching has been compared to sketching in VR, and it's been shown that the lack of a physical surface to rest your hand or stylus renders users more inaccurate at performing drawing-related activities. In terms of perception action coordination, Guillard's work serves to show that writing is inherently a bimanual task where the brain simultaneously controls both the non-dominant and the dominant hand to perform the task. And even though you can just perform the act with just your dominant hand, the non-dominant hand aids in detecting, analyzing, and integrating visual perceptual information. And it's been shown that in VR tasks that involve perception action coordination, self-representation with self-avatars really help. Arguliget's work highlights the importance of rendering the end effectors in a realistic manner to promote a higher sense of agency in fine motor pick and place tasks. And in general, it's been shown that VR-based training improves the psychomotor skills in the presence of self-avatars. So what's clear is that there's limited work that's compared perceptual motor performance in writing and art-related activities across real and immersive virtual environments. And furthermore, there seems to be a lack of work that's explored how the affordance of a self-avatar affects the performance of such tasks in VR. So this led us to our research thrust, where we wanted to ascertain where VR stands in being able to afford writing and art-related activities. So we conceptualized a 2-session between subject study where participants first experienced a digital input condition where they either were subjected to a condition with VR with 2 levels, VR with an embodied self-avatar, VR without a self-avatar, and real-world digital writing where they perform writing on an iPad. And in session 2, they performed the same writing and art-related activities that we'll describe later on a pen and paper approach, and we used session 2 and compared it to the outputs produced in session 1. So participants performed 4 tasks: writing within a boundary, writing without a boundary, tracing, and coloring. And we used Unity to come up with a writing interface for participants to enter their digital inputs and to come up with a scene for VR users to be immersed in while performing the tasks. And participants used the Wacom stylus and pen to perform writing in the VR conditions. And in the real world digital writing condition, participants performed the tasks on an iPad Pro. Participants wore the HTC Vive trackers and controllers to provide themselves with a self-avatar, and this is what it looked like.
Specifically,
we set the positions and the orientations of the key joints as constraints and apply the inverse kinematic to determine the remaining joint positions. We tracked the stylus by two different systems. When the stylus is close to the tablet, its position and orientation can be simply detected from the magnetic sensors. While this is not the case, the stylus is tracked by the wrist position.
A total of 45 participants took part in the study, 23 of which were female, 22, and the remaining were male. All of the participants we solicited for this study were right-handed and had corrected to normal vision. So participants were first briefed about what the experiment would involve, and then we measured their body proportions to calibrate them with a gender-matched body scaled self-avatar. And then each participant, for each participant, we calibrated a pen grip based on the way they held it. And then participants went through a body ownership phase where they stood in front of a virtual mirror and performed egocentric and exocentric pointing tasks to increase the sense of agency they felt with the avatar, if indeed they encountered a condition with the avatar. Participants then performed the tasks in the VR conditions, and then they took the NASA TLX questionnaire followed by the SUS presence questionnaire, following which they performed the same tasks on pen and paper. This marked the end of session 2, following which they engaged in semi-structured interviews where we probed into their perceptions of what the experience was like, and this marked the end of the study. So in terms of analysis, we used both objective and subjective measures. For our objective measures, we used image processing techniques to compute pixel error areas and perpendicular pixel error distances between the outputs produced in the digital conditions, as well as the real world pen and paper to make an objective comparison. We also solicited facilitators that were blinded to the conditions in which participants performed the writing and art-related activities and had them rate how similar it was to the outputs produced in the real world pen and paper paradigm. This is what we found. In terms of writing, there were no significant differences between the conditions, both writing within a boundary and writing without a boundary, in terms of how similar they were to the outputs produced in the pen and paper paradigm. So participants are more or less performed the same in terms of digital writing. In terms of coloring, we found a main effect of the condition and an object by condition interaction where object are the different objects that participant had to draw. And we found that in general, the mean error area associated with the real world digital condition was lesser than the VR conditions. In terms of how similar the raters rated them to the outputs produced in the pen and paper paradigm, we found, again, a similar trend with the RWI condition being rated as the most similar to the pen and paper paradigm. In the tracing task, again, we found a similar trend with the real world digital condition producing outputs most similar to the pen and paper paradigm. From our post interviews, we found that participants that experienced the condition with a self-avatar seemed to comment about occlusion issues they faced. And in general, the preference for real world digital inputs was preferred overall. So overall, we found that users seem to be less erroneous in performing writing and art-related activities in the real world as compared to them performing the same in VR. And we've also found that the affordance of a self-avatar didn't really seem to improve task performance, even though we postulated that it will based on the related work. So why is this the case? It may be that the use of an inverse kinematics model to animate the end effectors for performing such a fine motor interaction task might be insufficient. It may be that utilizing superior motion capture technologies to animate the end effectors may be required to see an effect of the. What does this all mean? There's still some way to go before we can say writing and art-related activities can be done as similarly in VR as it is in the real world. And it may be beneficial to investigate how higher fidelity motion capture technologies might help in performing such perception action coordination tasks. That's all for this talk. And I'd like to thank our team, a collaborative effort from Clemson University and National Chow Tong University. And thanks all.
Great. Thanks, Rohit, for the presentation, and sorry for getting the name wrong there at the beginning. Your Zoom name is Roshan, so and he's right there as well. So we're going to move to a Q&A session now, where I'll ask some questions in kind of a round robin style, and maybe we'll get into some deeper discussions and explore some connections between the papers as well. But let me start off with a question for Andre, back on the blank suppressed hand redirection paper. So the first question we have is from Ferran Argelaguet, and he says, this is a really interesting method and a great talk. And he asks whether you have assessed the amount of hand redirection that can be unnoticed during an eye blink when the user's hand is static. So I guess you only tested it while the hand was moving.
Yeah, very correct. I think first, thank you very much for the question. That's really, really good point. So we, in our work, only considered injecting hand offsets when the user is really in the reach motion, so moving the hand towards the target. And as I saw the question already in the chat, I just quickly looked up some details about that. And the hand, of course, was moving, but because reach motions are not that fast, it did not progress too much in our study. So users typically closed their eyes on average when they were 46% along the way towards the target, and reopened the eyes again when they were like 53% along the way. So they essentially progressed 7%. And in our distance, in our experiment, that means the hand moved by roughly 2 or 3 centimeters. So it's not exactly static, but close. But of course, if you investigate the purely static case, you would probably find some slightly different thresholds. And I think that would be a very interesting follow-up experiment and nicely complement the findings that we found in our study then.
Yeah, thanks, Andre. And maybe if I could just follow up on that briefly. Sure. So I was wondering, you know, when people are reaching in VR or in real life, they don't always look at their hands, right? But we have this kind of proprioceptive idea of where our hands are based on muscle activation and you know, knowledge of our joints and that sort of thing. I would think that proprioceptive cue for where the hand is located would be quite strong. And so I would have imagined that, you know, that this redirection would have been more noticeable. Why do you think it wasn't?
Well, in fact, that's very correct. You're right. The proprioception is very well, and especially with the hands, but still it's not perfect. And as we know from like cognitive research about multisensory integration, when we are really perceiving the hands both with our visual system and with our proprioceptive system at the same time. So when we look in the direction and have our hands in our visual field of view, then both the visual component and the proprioceptive component are combined and integrated. And the proprioceptive component will not have a weight, so to say, in this integration of 100% and override the visual information, but instead visual information, in fact, will change the overall percept and will have a certain contribution. And if you change the position of the visual rendering, then your overall percept will also change. And if this discrepancy then is not too big, then your cognitive process will basically not really recognize or alert to you any mismatch, but you will just believe that it is how you perceive it. And the perception is a mix of what you feel and what you see, which is manipulated then.
Yeah, visual dominance
exactly,
wins out
visual
in
dominance.
a lot of these illusions in VR for sure. Of course, I guess it depends on the user looking at their hand during the redirection, or the redirection
exactly.
is not going to work. Right.
In our case, we only studied this case. So of course, if you're like retarget the hand basically or manipulate anything while the hand is completely off track and you don't even see it, then results might be completely different. But in our kind of controlled experiment, users always had the hand somewhere in the visual area, but not in the focus. This is something I briefly mentioned it only in the talk. In our study, they should not look at the hand directly. As we prevented this, you can see the details in the paper, but we wanted to prevent the hand jumping into the visual focus area because this would be very noticeable.
Thanks.
Thank you.
So, Hugo, a question for you about the FlashPen paper. So I noticed in your results that there was this pretty consistent performance between the FlashPen prototype and the Wacom pen and tablet that you used as a comparison for several different metrics. And so if they perform similarly, can you just explain for us again why using a commercial device like the Wacom pen and tablet, which in fact was used in the last paper, is really insufficient for VR? What are the main advantages that the FlashPen prototype offers?
So first, I wouldn't say that it's insufficient to use such kind of commercial device in VR, because they bring, like, I would say, enough input precision to write, but most of the problem comes like it's constrained to the tablet that you need to carry everywhere, and it's constrained to the surface you need to write on. So for example, like in the pandemic where we are, it's kind of useful to have, big whiteboard where you want to collaborate with other people across the world. So you need a device where you can write on many surfaces, when you can write everywhere where you want. So that's when the idea came to design FlashPen, to have a device that could be used with any orientation and on any surfaces with the same quality than an analog pen. So
yeah, that's helpful. Thank you. And I guess just to stay on the same theme, Rohit and Roshan, and also Saab is here, another co-author of that last paper. So you found that people using the Wacom tablet in VR could do the tasks quite well, but not with as much speed or accuracy, right? And you kind of explained that based on kind of combination of visual and motor perception, and that there was a mismatch there. What do you think would be the requirements for a VR pen that would have close to real world performance?
In terms of a VR pen, what we were trying to get at was trying to see if the end effectors or the representation of your end effectors affect how your performance is in terms of looking at how writing in VR is done. So what we noticed was that in terms of similarities with the outputs that you produce when you're typically writing on a pen and paper or drawing on a pen and paper, users seem to be better at doing it on an iPad as compared to VR systems. So from our work, what we are able to see is that maybe leveraging higher fidelity animations towards making the end effectors represented better might help. We saw some marginal trends suggestive of that, but we need more investigations to actually confirm the same. But from our work, we were able to see that writing and art-related activities in VR is not yet at a point where it's seamless like it is on an iPad.
Hugo,
would just add to what Rohit and Roshan mentioned very briefly, that if we look at the error metrics, the objective error metrics that we gathered through image processing techniques, that is the error area, the error distance from the contour of the object that they were supposed to trace, or to what extent their writing actually went outside the boundaries that were presented to them that they had to write within. We found that those objective metrics were overall erroneous in the VR conditions, both in the presence and absence of embodiment as compared to the real world digital input. And one of the reasons, and it was first surprising to us, we hoped to find that when you had embodied interaction based on Yves Guillard's work, that you would have much more precision, and you would have these objective error metrics would show an improvement in the presence of a virtual hand holding a stylus that was an accurately scaled virtual hand of the dominant and non-dominant hand of the participant. But we found this effect where overall VR was much more erroneous as compared to the real world digital input. And we believe part of the reason is because of the lack of resolution with which they're able to see where they are writing in the head-mounted display-based viewing situation. And they were able to get, when the stylus nib came in contact with the surface, they have tactile feedback there. so that tactile feedback equivalently helped in the presence and absence of embodiment. But we found that it comes to viewing of your, it comes to receiving feedback of what you're writing and the viewing situation. So the lack of resolution, any latency with regards to your writing and your drawing and your tracing aspects on that surface can cause errors in your performance as compared to real world digital input, such as an iPad and stylus.
Yeah, that's really interesting. And I was going to ask Hugo, if in your experience, if you found the same thing, that it's not just the kind of accuracy of the pen-based input, but also the visual feedback that the user gets in VR that determines writing performance?
Yeah, I think I completely agree with what the other previous researcher said. Like, I think it's a whole body of research over here. I think it depends on the latency, it depends on the accuracy, it depends on the precision. It depends also on the task you are performing, because, you know, annotating a document is not the same as, for example, drawing like a large shapes on a whiteboard, or like sketching in midair, which is maybe less precise, but maybe more engaging. So yeah, I think such kind of behavior can be observed. Yeah.
Thanks. So let's move to a question for Sevinch on the authoring environment using the indirect interaction technique. So there's a couple of questions that are similar here, actually. So let me ask you that. So there's been previous VR systems that have used this interaction metaphor for manipulating objects or creating new objects or what have you. And they use a world in miniature paradigm, just like you did. But in a lot of those systems, the world in miniature was attached to the user's non-dominant hand, or if it wasn't attached to the hand, it was floating in space at the same orientation as the real world. So like in your case, the terrain would have been flat, whereas you chose to have a world in miniature that was floating and more like a map that was facing you. So can you talk about that design choice and how it might have affected usability?
Yeah, sure. So basically one of the reasons is that if it's attached to the non-dominant hand, then you have to basically keep your hand upright and do the interaction as such. That will cause tiredness. So that's why we thought, okay, that if we can put the panel 2D world in miniature freely in the world, and we can actually rest our arm on a chair or even on your body to do this gesture. So this will also apply if your world in miniature is not upright but on a flat, then you have to actually execute this gesture, and this will also cause tiredness. And and that's why we think that we think that this since we think that sitting position is a right for our application, because the scene authoring could take maybe hours. So you can sit on your chair, have your panel, and maybe rest your arm on a chair or on a table or on your body, and you can do this gesture without less fatigue, I would say.
I see. Thank you for that. Yeah, so it definitely depends on the posture of the user. Probably also depends on what the input device is. So with one of these pen-based devices that we've just been talking about, it might be more natural to kind of interact down here as if you were holding a clipboard and interacting with a pen. So there's subtle issues that determine which design is most appropriate. So thanks for that.
Thank you.
So Pedro, a question for you about the hands-free interaction. So this is from Esther, and she says, I'm just surprised that there are not any information source coming from hand gestures. I guess she's referring to your result about, kind of the most used modalities in the papers that you reviewed. And so hand gestures obviously would not have been part of your review because you were talking about hands-free.
Yes, exactly. I did not mention it in the presentation, but
Yeah.
It's mentioned in the manuscript, and we defined hands-free as every interaction that does not use the hands. So hand
Sure.
gestures are not.
So maybe let me just follow up on Esther's question and ask, did you see any examples of using gestures from other body parts? So head gestures, eye gestures,
Yes.
for example.
Yeah. For eye and head, we noticed that a few studies, maybe like a couple, use the head movement, not the head gaze, or the eye movement and not the eye gaze. So just swiping with eye, swiping with the head. And also we found one study that used foot movement. So participants had their feet in kind of like a surface that acted like a mouse, and then they could move the cursor in the immersive environment. But also body positioning. Some studies use like the place where the user was in the world to select objects in a menu, for instance.
Oh, that's interesting. Thank you. So let me go back to Andre. We have a few more minutes left for the Q&A, and there's several questions for Andre's paper. So Michael Serino says, I'd like to know if participants always blinked for every selection, I guess in your study, he's asking. And if not, do you think it significantly affects the results? And I guess I had a similar question, which is, if you were going to implement this in practice, what do you do if the user doesn't blink during the reaching motion?
Yeah, that's a very good question, and I cannot answer it because we don't know what's the best way, what's the best thing to do yet. That's not what we studied in this paper. So concerning the very first question, unfortunately, no, users do not blink during every reach motion. That's what we very quickly found out. And in this study, however, we still think that there will be universally applicable and very useful techniques in the future that builds on this idea of blink suppressed hand redirection. And so for this study, we decided to just study the blink suppressed part of this technique. And we essentially only analyzed trials where users validly blinked during the reach to determine the detection thresholds. And so in our analysis, everybody blinked essentially. However, in practice, this, as I said, doesn't work. And I think 1/3 of the trials we had to discard at the end, because in 1/3 of the trials, users reached but didn't blink in a valid way, let's say. And the very good question for follow-up work is now what to do in those cases. And as I very briefly sketched at the end of the talk, and we also have some ideas in the paper in written form, one idea would be to build in something like a fail-safe mechanism that maybe detects or recognizes when a user does not blink after, let's say, 60% progress towards the target, and then does something to still ensure that the user reaches the target. For example, boosts the redirection at the very end, sacrificing unnoticeability potentially, but still ensuring that the user really ends up where the user should end up. That is one way. But another way, which is what we are currently studying, is if there's a way to trigger blinks on demand and let the system somehow do some visual manipulation that induces a blink in the user and lets the user blink whenever the algorithm needs a blink to occur. And I think that's a very interesting avenue that we want to look into in the next time.
Yeah, that's a really interesting possible approach. You can't rely on these things happening and guarantee that they're going to happen when you want them to, but maybe inducing them would work.
And if there would be something like a blink trigger mechanism, I think that would be very useful also for other techniques like redirected walking that have been shown to make use of blinks, and that could also then profit from something like a trigger mechanism. Yeah. So let's see.
Thanks, Andre. I think we have time for maybe one more question, and I see one more for Sevinch here. So actually it's two questions, but they're both about metrics. So we were talking a second ago about hand positioning and tablet positioning and fatigue and so on. And so the question is, did you measure fatigue and did you measure simulator sickness in your study?
We did actually measure similar. Our participants has to answer before and after simulator sickness questionnaire. We reported the values, but what we also realized and were expecting, some of the participants reported, said during the study felt sick, doing this basically gesture zoom out with the two-handed gestural input. And for the fatigue, we basically gave in our subjective questionnaire, we asked them to rank how fatigue for them after each of the conditions. And we actually did not find any significant difference between them.
All right, thank you. Well, we are at the end of our time for this session, so I want to thank all the authors and presenters, and thank you for this great discussion. Thanks to all the audience who watched this as well. Hope you enjoy the rest of the conference. Thank you all.
Okay, good afternoon, everybody. Welcome to Speed Dating. My name is again Joaquim Jorge, and I'm going to tell you about this fantastic opportunity. So what is scientific speed dating? It's an opportunity to meet up to 8 new colleagues or attendees in the next hour. And where is this going to take place? You go to the speed dating arena that used to be called Workshop Square in Verbella, and it's happening right now. So this is what it looks like. It has a bunch of rooms, and each of those rooms you can sit. The more senior people are welcome to sit. So for instance, Professor Doug Bowman or Professor Tabitha Peck or are welcome to sit in one of the rooms, and the rest of the people circulate around. So how does it work? We have structured rooms where you can talk about you and your research interests to a colleague. And how does it work? We are aiming at 8 rounds of 5 minutes. If this works well, we can do better than that. After each round, we exchange partners. You will talk to at least 8 new people in the next 40 minutes. And so how does it go? Each person walks into an office from 1 to 36. If it's empty and you are a senior person, you sit and wait for a pair. Else, if there is one person inside, sit to talk. Of course, you're welcome to talk to other people already sitting. Else, if there is already a pair, move to the next room. Use 5 minutes to discuss. How do you get there? You will notice that there is a new item in the workshop square called offices. You click on offices, you get a drop-down menu with 36 names of interesting Portuguese cities and with decoration to match. And after 5 minutes, you change partners. One of you remains seated and the other one moves to the next office. One moves to 2, 2 moves to 3, last one moves to first. The one that moves every round. The one that stays every round. After 8 rounds, you have met 8 new researchers. So these are the summary instructions. Enjoy the dating. I hope, unless somebody here has any questions, I'll meet you there. Or as they say in the States, be there or be square.